Hello there, and welcome. Tonight I want to take you somewhere extraordinary, somewhere that doesn't quite exist in the way we normally think about existence, yet somewhere that might teach us something profound about the universe we actually inhabit. Before we begin this journey together, I'm curious about you, about where you are right now as these words reach you through the darkness. Perhaps you're lying in bed, the weight of the day finally releasing from your shoulders, or maybe you're sitting in a comfortable chair, the world outside your window settling into its nightly rhythm. What time is it where you are? Is it that precious hour when the sky has just surrendered its last light? Or are you in the deep middle of the night when the world feels most quiet, most receptive to wonder? Whatever corner of our planet you're listening from, whether it's a bustling city where lights never truly dim, or a quiet countryside where stars peek through with ancient brightness, you're part of this moment we're creating together. And if you find yourself drifting along with these thoughts, if this journey into cosmic mystery feels like something you'd want to return to on other nights, when sleep seems distant and your mind craves gentle exploration, perhaps you might consider subscribing. Leaving a quiet like that helps this little sanctuary of calm continue to exist. Share it with someone who might need this peaceful escape, someone whose mind, like yours, sometimes needs permission to wander through the vastness without urgency, without fear. These small gestures help ensure that this space remains here, waiting for you whenever you need to step away from the rush of daily life and into something slower, something that moves at the pace of stars and galaxies rather than deadlines and obligations. You know, there's something remarkable about the fact that you and I can share this moment despite being separated by distance, perhaps by continents and oceans, yet connected through this simple act of contemplation. We're about to explore an idea that sounds impossible at first, maybe even nonsensical, but I promise you that by the end of our time together, it will have changed something subtle about how you see the cosmos and your place within it. The question we're going to explore tonight isn't one that keeps scientists awake with worry, isn't one that threatens or alarms. Instead, it's a question that invites us to turn our understanding inside out, quite literally, and in doing so, discover new ways to appreciate the magnificent universe we actually live in. Let me begin by reminding you of something you probably already know, something that has become so fundamental to our understanding of the cosmos that we rarely stop to marvel at its strangeness anymore. Our universe is expanding. Right now, as you lie there listening to my voice, as your breath moves gently in and out, as your heartbeat maintains its steady rhythm, the very fabric of space itself is stretching. Galaxies that are millions of light years away from us are moving farther away, not because they're traveling through space like ships through an ocean, but because space itself is growing, creating more room between everything that exists. It's like a loaf of raisin bread rising in an oven, where the raisins aren't moving through the dough, but the dough itself is expanding, carrying the raisins apart from each other. Or perhaps imagine dots drawn on the surface of a balloon, and as someone inflates the balloon, those dots move away from each other, not because they're sliding across the surface, but because the surface itself is growing. This discovery, which we owe to astronomers like Edwin Hubble, who first noticed that galaxies seem to be racing away from us in all directions, fundamentally changed how we understand our cosmic story. It told us that the universe had a beginning, a moment we call the Big Bang, when all of space was compressed into an unimaginably small point, and then began this grand expansion that continues to this day. Scientists have measured this expansion with extraordinary precision, using the light from distant galaxies, the faint afterglow of the Big Bang itself that we call the cosmic microwave background, and the brightness of exploding stars called supernovas that serve as cosmic lighthouses marking distances across the void. But tonight, in this quiet space we're sharing, I want to invite you to imagine something different, something that goes against everything we've just discussed. Not because I'm suggesting our universe actually works this way, but because sometimes the best way to understand something is to imagine its opposite. It's a question that might sound like a mistake at first, like someone got confused about which direction things are supposed to go, but the more we sit with it, the more it gently tugs at our curiosity, revealing hidden assumptions we didn't even know we were making. What if, instead of expanding outward, the universe expanded inward? What if space itself, rather than stretching and growing, was somehow folding in on itself, drawing everything not apart but together in a way that defies our normal understanding of what inward even means when we're talking about the entire universe? I know this sounds paradoxical, maybe even impossible, and in many ways it is. Our universe doesn't work this way, and we have mountains of evidence to prove it. But that's not the point of our journey tonight. We're not here to overturn scientific understanding, or to propose some radical new theory that physicists have somehow missed. Instead, we're here to play with an idea, to let our minds wander through a thought experiment that might seem silly at first, but gradually reveals itself to be a profound meditation on space, time, and our place in the cosmic order. Think of it as a kind of cosmic poetry, a what-if story that helps us see our actual universe with fresh eyes. The way that reading fantasy can sometimes help us better understand reality, or the way that dreaming about flying can make us more aware of the sensation of our feet on solid ground. When we talk about the universe expanding outward, we're describing something that happens everywhere at once. There's no center to this expansion, no special point in space from which everything is moving away. Every galaxy, every star, every atom in the universe experiences itself as stationary while seeing everything else moving away. It's a difficult concept to grasp because our everyday experience tells us that explosions have centers, that things that expand must be expanding from somewhere into somewhere else. But the universe doesn't expand into anything. Space itself is what's expanding. There's no outside into which it grows, no container that's getting fuller. The universe is all there is, and it's getting bigger not by claiming new territory, but by creating more space within itself. Now, when we imagine an inward expansion, we're not simply reversing this process, we're not talking about the big crunch, which is the idea that the universe might someday stop expanding and begin contracting, eventually collapsing back into a point. That's a different concept entirely, one that scientists have considered and largely ruled out based on observations showing that the expansion is actually accelerating. No, what we're imagining tonight is something stranger, something that requires us to think about inward in a new way. What if inward didn't mean toward a center, but toward something else entirely, something that exists at every point in space simultaneously? Picture yourself standing in a vast field at night, looking up at the stars. In our universe, those stars are moving away from you, carried by the expansion of space itself. But in our imagined inward expanding universe, those stars would be moving toward you, yet not just toward you specifically. They would be moving toward every point in space at the same time, as if every location in the universe was simultaneously the center toward which everything flows. It's a mind-bending concept, one that seems to violate our basic understanding of geometry and direction, yet it's not entirely without precedent in physics. The mathematics that describe curved space-time, the same mathematics that Einstein used to explain gravity, allow for all sorts of strange geometries that our three-dimensional brains struggle to visualize. Think about the surface of the Earth for a moment. If you start walking north from anywhere on the planet, you'll eventually reach the North Pole. Every northward path, no matter where it starts, converges on that single point. Now imagine something similar but more complex, where instead of having just one pole, every point is simultaneously a pole toward which all paths converge. It's impossible to visualize properly, but mathematics allows us to describe such spaces, to work with them, to understand their properties even if we can't picture them in our minds. This is the kind of space we're imagining when we talk about inward expansion, without a center, a space where inward is a direction that exists everywhere and leads everywhere. As we continue this thought experiment, we'll need to be gentle with our expectations of understanding. The human brain evolved to navigate a world of solid objects and clear directions, of up and down, left and right, forward and backward. We're not equipped to intuitively grasp the curved geometries of space-time or the paradoxes of infinity. But that's okay. In fact, it's more than okay. It's part of what makes this exploration so wonderfully relaxing. We don't need to fully understand. We don't need to solve any problems or reach any conclusions. We can simply let these ideas wash over us like waves on a beach, each one bringing something new to contemplate, each one receding to make room for the next. The universe we're imagining tonight, this inward expanding cosmos, would be a place of gathering rather than dispersal, of coming together rather than moving apart. But it wouldn't be a violent collapse or a catastrophic crunch. Instead, it would be a slow, gentle drawing together, like a vast cosmic breath being drawn in so slowly that billions of years would pass without any noticeable change. Galaxies would drift toward each other with infinite patience, their light growing imperceptibly brighter as the space between them quietly contracted. Stars would continue their ancient burning, planets would continue their steady orbits, and life, if it existed in such a universe, would go about its business, perhaps never even noticing the slow inward tide of space itself. In our actual universe, we've discovered that not only is space expanding, but the expansion is accelerating. Galaxies are moving apart faster today than they were yesterday, and they'll be moving apart even faster tomorrow. This acceleration is driven by something we call dark energy, a mysterious force or property of space itself that acts like a kind of anti-gravity, pushing everything apart. We don't really understand what dark energy is, only that it makes up about 68% of the total energy in the universe, and that without it, gravity would have long ago begun to slow the expansion, perhaps eventually reversing it. In our inward expanding universe, we might imagine something like the opposite of dark energy, a force that gently pulls rather than pushes, that encourages gathering rather than scattering. Not a force that crushes or destroys, but one that simply makes space prefer to be close rather than far, intimate rather than distant. The geometry of such a universe would be fascinating to contemplate. In our expanding universe, we talk about the observable universe, the sphere of space from which light has had time to reach us since the Big Bang. Beyond this sphere, there are presumably more galaxies, more stars, more space, but we can't see them because their light hasn't had time to reach us yet, and because of the expansion, some of it never will. The observable universe is like our cosmic horizon, the limit of what we can know directly through observation. In an inward expanding universe, this horizon would behave differently. Perhaps distant galaxies would gradually come into view as space contracted, revealing more and more of the cosmos as time went on. The universe would slowly unveil itself, like a gradually lifting fog revealing an ever richer landscape of stars and galaxies. Time itself might flow differently in such a universe, or at least our perception of cosmic time would change. In our universe, we look out into space and back into time, seeing distant galaxies as they were billions of years ago, when their light began its journey toward us. The expansion of space means that the most distant objects we can see are also the youngest, showing us the universe as it was in its infancy. In an inward expanding universe, this relationship between distance and time would be altered in subtle ways. The past wouldn't recede from us quite so dramatically. Ancient light would arrive with more of its original energy intact, carrying clearer messages from the early cosmos. As you lie there, perhaps feeling your own breath naturally slowing as these ideas spiral through your mind, consider how this inward expansion might feel if you could somehow sense it directly. Of course, the effect would be far too slow to perceive, taking billions of years to produce noticeable changes. But imagine if you could feel it, the way you can feel the tide gradually rising on a beach, or the way you can sense the slow turning of the seasons. It might feel like a gentle gathering, a soft pulling that's not uncomfortable or urgent, just a steady, patient drawing together of all things. Your body, held together by its own molecular forces, wouldn't feel this cosmic inward flow any more than you currently feel the outward expansion of space. You would remain yourself, intact and whole, while the larger universe slowly, gently reorganized itself around you. This brings us to an important point about scale. The forces that govern our daily lives, the electromagnetic forces that hold atoms together, the strong nuclear force that binds atomic nuclei, even gravity on the scale of solar systems and galaxies, these forces are far stronger than the cosmic expansion, or, in our thought experiment, the cosmic contraction. That's why you don't expand along with the universe, why the Earth doesn't grow larger as space stretches, why galaxies hold together despite the expansion happening all around them. Only on the very largest scales, across millions and billions of light years, does the expansion or our imagined contraction become the dominant force. It's like a whisper that's too quiet to hear in a noisy room but becomes audible in perfect silence. A force so gentle that only the vastness of empty space allows it to express itself. In this inward expanding universe, we might imagine civilizations arising on countless worlds, looking up at their night skies and gradually coming to understand the nature of their cosmos. But instead of discovering that everything is moving away, racing toward an ever more dilute future, they would find that the universe is slowly gathering itself, that distant galaxies are approaching, that the cosmos is engaged in a grand, slow-motion embrace. How would this discovery shape their philosophies, their religions, their understanding of meaning and purpose? Perhaps they would see the universe as fundamentally hospitable, as moving toward unity rather than isolation. Perhaps their myths would speak of a cosmic homecoming, a gradual return to some primordial wholeness. We can imagine their scientists making measurements similar to ours but finding different results. When they analyze the light from distant galaxies, they wouldn't see the redshift that our astronomers observe, that stretching of light waves that tells us space is expanding. Instead, they might see a blue shift, a compression of light waves indicating that space is contracting. Their cosmic microwave background, that faint afterglow of their Big Bang, would be slowly shifting toward higher energies rather than cooling toward absolute zero. They would live in a universe that's growing warmer rather than colder, denser rather than more dilute, more connected rather than more isolated. But let's be clear, this warming wouldn't be dangerous or threatening. We're not imagining a universe racing toward a fiery doom, but one that's simply moving in a different direction from ours, and doing so with such incredible slowness that billions of years would pass with barely perceptible change. Stars would still live out their long lives, converting hydrogen to helium, helium to carbon, building the elements that make planets and life possible. Galaxies would still spin their majestic spirals, stellar nurseries would still give birth to new stars, and planets would still orbit in the quiet darkness, some of them perhaps harbouring the spark of consciousness, the miracle of awareness. The philosophical implications of living in such a universe would be profound. In our expanding cosmos, we face what some call the heat death, a far future when all the stars have burned out, when black holes have evaporated, when the universe has spread itself so thin that nothing interesting can ever happen again. It's a melancholy vision, though one so distant that it needn't trouble us. But in an inward expanding universe, the far future might look different. Not a heat death, but perhaps a gathering of possibilities, a concentration of cosmic potential. Not an ending, but a transformation into something we can't imagine, something that transcends our current understanding of physics and cosmology. As we prepare to delve deeper into this thought experiment in the coming chapters, to explore how light and time and gravity might behave in such a universe, let's take a moment to appreciate the sheer audacity of what we're doing. Here we are, tiny conscious beings on a small planet orbiting an ordinary star in one galaxy among trillions, and we're imagining alternative universes. We're playing with the fundamental structure of reality itself. Not because we must, not because there's any practical benefit to it, but simply because we can, because our minds are capable of this kind of cosmic play, this kind of boundless wandering. The fact that you're here, choosing to spend your time contemplating these impossible possibilities, says something beautiful about human nature. In a world that often demands immediate practical results, that values productivity over contemplation, you've chosen to lie back and wonder about something that has no immediate application, no obvious benefit except the pure joy of thinking, of imagining, of exploring ideas for their own sake. This is a kind of rebellion, a gentle insistence that not everything needs to be useful, that sometimes the most important things we do are the ones that serve no purpose except to remind us that we're more than our daily routines, more than our practical concerns, more than the small urgent matters that usually occupy our thoughts. As this first chapter draws toward its close, as we prepare to journey deeper into our inside-out universe, I want you to notice how your body feels right now. Perhaps there's a heaviness settling into your limbs, a comfortable weight that comes from letting go of the need to be anywhere else, to do anything else. Your breathing has probably slowed without you noticing it, falling into rhythm with the unhurried pace of these cosmic contemplations. This is exactly as it should be. We're not racing toward any conclusion, not trying to solve any urgent problems. We're simply floating together through an idea, letting it carry us wherever it wants to go. In the chapters ahead, we'll explore what it means to turn space inside out, how time might flow in such a universe, how light would behave, what kinds of worlds and possibly even what kinds of life might exist there. We'll compare our imaginary cosmos to the real one, seeing how scientists actually measure the expansion of space and what those measurements tell us. we'll think about consciousness and meaning in an inward expanding universe, about how the experience of existence might differ from our own, and eventually, gently, we'll return to our own cosmos, carrying with us whatever insights or simply whatever sense of peace this journey has provided. But for now, in these last moments of our first chapter together, I want you to hold on to this image. Somewhere, in the space of all possible universes, there might exist a cosmos that expands inward rather than outward, where space itself is engaged in an eternal gathering rather than an eternal dispersal. It's a universe we'll never visit, never observe, never prove or disprove. But by imagining it, by taking the time to think through its implications, we're doing something profoundly human. We're using our imagination not to escape reality, but to better appreciate it, to see our own universe with fresh eyes, to remember that even the most fundamental facts about existence are, in some sense, miraculous. The universe expands outward, yes, but it could have been otherwise. The laws of physics are what they are, but they could have been different. We exist in this cosmos at this time, able to contemplate these mysteries, and that too could have been otherwise. The sheer improbability of our existence, of consciousness arising in a universe that seems to have no need for it, of matter organizing itself into patterns complex enough to wonder about other patterns. This is the real mystery, the one that underlies all our scientific questions and philosophical wanderings. So as we move forward into the deeper waters of our thought experiment, remember that we're not trying to reach any final answer or ultimate truth. We're simply exploring, the way a child might explore a garden, not to map it or catalogue it, but simply to see what's there, to feel the texture of leaves, to watch the play of light through branches, to discover whatever wants to be discovered. Our inward expanding universe is like a garden of ideas, a space where we can wander without purpose, without pressure, without any need to achieve anything beyond the simple pleasure of wandering. And perhaps, as you drift closer to sleep tonight, or on whatever night you return to these thoughts, you'll carry with you this gentle paradox, a universe that expands inward, a cosmos that grows by gathering, a reality that moves in impossible directions that somehow, in the quiet space of imagination, make perfect sense. Let it be a kind of koan, a puzzle not meant to be solved but simply held, turned over in the mind like a smooth stone in the pocket, a reminder that reality is stranger than we know, that mystery is not a problem to be eliminated but a gift to be treasured, that sometimes the most restful thing we can do is to think about things too large for thinking, to imagine things too strange for imagining, to expand inward into the infinite space of our own wandering minds. And so we continue, drifting deeper into this impossible thought, this gentle paradox of an inward expanding universe, and perhaps you're finding that the strangeness of it is beginning to feel less jarring, less like a mistake, and more like a different kind of music, played in a key we're not used to hearing. Let's return for a moment to those familiar analogies we use to understand our own universe's expansion, the images that scientists and teachers have crafted to help our three-dimensional minds grasp something that properly exists in 4 dimensions or more. You remember the balloon, don't you? That simple rubber sphere with dots drawn on its surface, and as someone breathes into it, the balloon swells and those dots move apart from each other, not because they're sliding across the rubber, but because the rubber itself is stretching, creating more surface, more space between every point and every other point. It's such a comforting image in its simplicity, something a child could understand, and yet it captures something profound about the nature of our cosmos. Every dot on that balloon surface could consider itself the center of the expansion, watching all other dots recede from it at rates proportional to their distance. The farther away another dot is, the faster it appears to be moving away, not because it's actually moving faster, but because there's more expanding space between them, more stretching happening across that greater distance. This is exactly what we observe in our universe when we look at distant galaxies, finding that the ones farther away show greater redshift, their light stretched more dramatically by all the expanding space it had to cross to reach us. Or perhaps you prefer the raisin bread analogy, that warm, yeasty image of dough rising in an oven, carrying raisins apart as it expands. Each raisin, like each galaxy, stays the same size, held together by its own internal forces, but the space between raisins grows as the dough swells with heat and fermentation. It's a cozy way to think about cosmic expansion, something that brings the incomprehensible scale of the universe down to kitchen size, to something you could hold in your hands, something you could slice and eat with butter while contemplating the nature of infinity. But now, in our quiet thought experiment, we need to take these familiar images and somehow turn them inside out, and this is where language begins to struggle, where our normal ways of thinking start to bend and fold in unexpected ways. How do you reverse the expansion of a balloon? Your first thought might be to let the air out to watch it deflate, but that's not quite what we're after. That would be a collapse, a shrinking, everything racing toward a single point. What we're imagining is stranger than that, more subtle, more paradoxical. We're imagining a balloon where the surface somehow expands inward, where becoming bigger means becoming more interior, more enclosed, more gathered, even as every point on the surface maintains its relationship to every other point. Perhaps we need a different analogy altogether, something that captures this sense of inward movement without collapse. Imagine standing at the edge of a vast ocean, watching waves roll toward the shore. Now imagine that every point on the ocean's surface is simultaneously a shore, and waves are rolling toward every point from every other point. It's impossible to visualize properly, this ocean where every location is both source and destination, where the movement is always inward no matter where you are or which direction you look. Yet mathematically, such a space could exist, could be described with equations, could have properties we could study even if we could never properly picture it in our minds. The mathematics of curved space-time, the same mathematics Einstein used to describe gravity, allows for geometries that our everyday experience never encounters. In our normal, flat understanding of space, parallel lines never meet. The angles of a triangle always add up to 180 degrees, and the shortest distance between 2 points is a straight line. But on curved surfaces, in curved spaces, these rules change. On the surface of a sphere, for instance, parallel lines do meet. Triangles can have angles that sum to more than 180 degrees, and the shortest path between points is along a great circle, like the flight paths airplanes take across the globe. Now imagine a space with even stranger curvature, where the geometry is neither flat nor simply spherical, but something more complex, something that curves inward at every point simultaneously. Mathematicians call these negative curvature spaces, and they have properties that seem almost magical to our flat space intuitions. In such a space, there's more room than there should be. You could draw a circle and find that its circumference is larger than a 2p times its radius, as if the space inside the circle somehow contained more area than a flat circle of the same size should contain. It's like those impossible drawings by M.C. Escher, where staircases go up forever while somehow returning to where they started, where water flows uphill, where the inside becomes the outside and the outside becomes the inside. In our inward expanding universe, we might imagine space itself having this kind of negative curvature, but a dynamic negative curvature that increases over time. Every point in space would be developing more inwardness, more interior dimension, even as the relationships between points remained consistent. It's as if space itself were becoming deeper rather than wider, more layered rather than more spread out, like a simple melody gradually becoming a rich harmony, adding inner voices and resonances without getting louder or longer. Think about a sponge for a moment, one of those natural sea sponges with all its intricate channels and passages. Now imagine that sponge beginning to develop more internal structure, more passages, more complexity, but without getting any bigger on the outside. In fact, imagine it slowly, gently compressing. But as it compresses, it develops even more internal space, more hidden dimensions, more secret passages. The sponge becomes denser, not in the sense of having less room inside, but in the sense of having more structure, more organization, more internal relationships. This is something like what we're imagining for our inward expanding universe, a cosmos that grows not by spreading out, but by developing more internal complexity, more hidden dimensions, more space folded within space. The flow of such a universe would be unlike anything in our experience. In our expanding cosmos, if you could somehow stand still relative to the cosmic expansion, you would see all distant galaxies flowing away from you like boats carried by an outgoing tide. But in our inward expanding universe, those same galaxies would be flowing toward you, yet not just toward you specifically. They would be flowing toward every point simultaneously, as if every location in space were a drain, and all of space were water spiraling down, but spiraling down everywhere at once, with no actual drainage point, no final destination, just an eternal inward flow that never reaches a centre, because every point is equally the centre. It's helpful here to think about what physicists call the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. Homogeneous means it's roughly the same everywhere, that one region of space isn't fundamentally different from another. Isotropic means it looks the same in all directions, that there's no special direction, no cosmic arrow pointing towards something unique. Our expanding universe obeys this principle, which is why there's no centre to the expansion, no special location from which everything is moving away. Our inward expanding universe would need to obey the same principle, which is why the inward flow happens everywhere equally, why every point experiences itself as the centre of the inward motion. This might seem to violate our basic understanding of what inward means. After all, inward implies toward something, toward a centre, toward an interior. But in the curved space-time we're imagining, inward becomes a local direction that exists everywhere, like down on the surface of the Earth. No matter where you stand on our planet, down points toward the centre of the Earth, but if you're on opposite sides of the globe, your down directions point in opposite directions relative to each other, yet both are equally valid, equally real. In our inward expanding universe, inward would be like this, a direction that exists everywhere but points differently depending on where you are, yet somehow all these different inward directions are part of the same cosmic flow. Let's think about how this might look if you could somehow see it happening, if the billions of years of cosmic evolution could be compressed into moments you could observe. Imagine floating in space, far from any galaxy, in the vast emptiness between cosmic structures. In our universe, if you could wait long enough, you would see the distant galaxies gradually dimming, their light shifting toward red, eventually disappearing beyond the cosmic horizon as expansion carries them away faster than light can travel. But in our inward expanding universe, you would see something quite different. Those distant galaxies would gradually brighten, their light shifting toward blue, more and more galaxies appearing from beyond what was previously the cosmic horizon, the universe revealing more of itself as space contracts and brings distant light within reach. But here's where it gets truly strange. Even as those galaxies appear to approach you, an observer in any of those galaxies would see the same thing. They would see you and all other galaxies approaching them. Everyone would experience themselves as the stationary centre toward which everything else flows, just as in our expanding universe everyone experiences themselves as the stationary centre from which everything else recedes. It's a perfect symmetry, just inverted, turned inside out like a glove, but maintaining all the same relationships, all the same fundamental structures. The rate of this inward expansion would follow its own laws, its own cosmic rhythm. In our universe, we've discovered that the expansion rate isn't constant, but has changed over cosmic history. In the early universe, radiation dominated and the expansion gradually slowed. Then matter became dominant and the expansion continued to slow but at a different rate. And now, in our current epoch, dark energy has become dominant and the expansion is accelerating. Our inward expanding universe might have its own epochs, its own phases of evolution. Perhaps there would be an early phase of rapid inward expansion, followed by a gradual slowing, and then perhaps an acceleration driven by some kind of dark compression, a force that pulls space together just as dark energy pushes it apart. We could imagine scientists in this universe making discoveries parallel to our own but inverted. Where Edwin Hubble discovered that galaxies are receding from us, their version of Hubble might discover that galaxies are approaching. Where our cosmologists found evidence for dark energy in the brightness of distant supernova, theirs might find evidence for dark compression in similar observations. Where we worry about the heat death of the universe, the gradual dissipation of all energy into an ever-expanding void, they might contemplate a different far future, one where the universe gradually gathers all its energy into ever more complex structures. The concept of distance itself would take on new meanings in such a universe. In our cosmos, we speak of proper distance, the distance between objects at a specific moment in cosmic time, and comoving distance, which factors out the expansion of space. In an inward expanding universe, these same concepts would exist but with different implications. Proper distances would decrease over time as space contracts, but comoving distances might remain constant. providing a stable framework for describing the universe's structure. It would be like having a map that stays the same size even as the territory it represents slowly shrinks, maintaining all the same relationships and proportions but at an ever smaller scale. Temperature and energy would behave differently too. In our expanding universe, the cosmic microwave background radiation, that faint afterglow of the Big Bang, is cooling as space expands, stretching the wavelengths of those ancient photons until they barely carry any energy at all. In an inward expanding universe, this radiation would be slowly warming, its wavelengths compressing, its energy gradually increasing. Not dramatically, not dangerously, but steadily over cosmic time. The universe would be slowly gathering its energy rather than dispersing it, concentrating rather than diluting its primordial heat. This brings us to entropy, that measure of disorder that, according to the second law of thermodynamics, always increases in closed systems. In our universe, entropy increases as energy spreads out, as hot things cool down, as ordered structures gradually decay into randomness. But in an inward expanding universe, the relationship between entropy and cosmic evolution might be more complex. The compression of space might create new opportunities for order to emerge, new ways for energy to organize itself into complex structures. It wouldn't violate the second law of thermodynamics, but it might express it differently, finding new paths toward maximum entropy that involve gathering rather than dispersal. Consider how gravity would work in such a universe. In our cosmos, gravity pulls matter together locally, creating stars, planets, and galaxies, while the cosmic expansion pulls everything apart on the larger scales. It's a kind of cosmic tension, a competition between gathering and dispersing forces. In an inward expanding universe, gravity and the cosmic contraction would work together rather than in opposition. Both would encourage gathering, clustering, the formation of ever more complex structures. Galaxies might form earlier and grow larger. Clusters of galaxies might be more tightly bound. The large-scale structure of the universe, that vast cosmic web of filaments and voids that we observe, might be denser, more intricate, more interconnected. Yet despite all these differences, the fundamental laws of physics would remain the same. Atoms would still be atoms, held together by electromagnetic forces. Stars would still shine by nuclear fusion, converting hydrogen to helium and releasing energy in the process. Planets would still orbit their stars according to the laws of gravity. Chemistry would work the same way, allowing for the complex molecules that make life possible. The inward expansion would be a background effect, a cosmic stage on which the familiar dramas of stellar evolution, planetary formation, and possibly biological evolution would still play out. As you lie there, perhaps feeling your thoughts beginning to curve inward themselves, folding gently towards sleep, consider how this different cosmic geometry might affect the experience of living beings within it. Would they feel the inward pull, some subtle sense that space itself is gathering around them? Probably not, just as we don't feel the outward expansion of our universe. The effect is too slow, too gentle, too large-scale to impinge on daily experience. But perhaps there would be some deep, unconscious awareness, some feeling of cosmic embrace rather than cosmic isolation, of being held rather than being cast adrift. Their philosophies might develop differently, shaped by this different cosmic context, where our existential concerns often involve feelings of cosmic loneliness, of being tiny isolated beings in a vast expanding void. Theirs might involve different questions. Perhaps they would wonder about the implications of eternal gathering, about what it means to live in a universe that's always drawing together, always becoming more interconnected, more unified. Their religions might speak of a cosmic reunion rather than a cosmic separation, of a universe moving toward unity rather than toward isolation. The mathematics they would develop to describe their universe would be familiar yet different, like a piece of music transposed to a different key. The equations of general relativity would still apply, but with different solutions, different metrics describing the shape of space-time. Where we use the Friedmann, Lemaitre, Robertson, Walker metric to describe our expanding universe, they would use a modified version describing contraction. Where we calculate the Hubble constant to measure the rate of expansion, they would calculate something like an anti-Hubble constant to measure the rate of contraction. Even the way they would visualize their universe might differ from ours. We often use embedding diagrams, pictures that show how space-time curves, by imagining it embedded in a higher dimensional space. our expanding universe is sometimes visualized as the surface of an expanding balloon or bubble. Their contracting universe might be visualized as something folding inward, perhaps like those origami sculptures that seem to contain infinite complexity within a finite form, always revealing new interior spaces as you unfold them, except in their case, the universe would be folding rather than unfolding, creating new interior dimensions rather than revealing pre-existing ones. The horizon problem, one of the puzzles that led to the theory of cosmic inflation in our universe, would manifest differently in theirs. In our cosmos, regions of space that have never been in causal contact with each other show remarkably similar properties, suggesting that they were once connected in ways our standard expansion model doesn't easily explain. In an inward expanding universe, the opposite problem might arise. Regions that should be in causal contact might show unexpected differences, requiring their own version of inflation theory to explain how the universe could maintain its large-scale uniformity while contracting. Dark matter, that invisible substance that makes up about 27% of our universe, would play its role in their cosmos too, but perhaps differently. In our universe, dark matter helps explain how galaxies formed so quickly after the Big Bang and why they rotate the way they do. In an inward expanding universe, dark matter might be even more important for structure formation, its gravitational pull working in concert with the cosmic contraction to build galaxies and clusters. Or perhaps they would need less dark matter to explain their observations, since the background contraction would already be helping to gather matter together. As we near the end of this contemplation of inside-out space, it's worth pausing to appreciate the sheer strangeness of what we've been imagining. We've taken one of the most fundamental facts about our universe, that space itself is expanding, and we've inverted it, turned it inside out, reversed it in a way that maintains all the symmetries and principles we hold dear, while creating an entirely different cosmic story. It's like looking at a familiar photograph through its negative, where all the darks become lights, and all the lights become darks, yet the image remains recognizable, still showing the same scene but transformed, inverted, made strange and new. This kind of thinking, this willingness to imagine alternatives to even the most basic facts about reality, is part of what makes us human. We're not content to simply observe and catalogue the universe as it is. We want to understand why it's this way and not another way, what other ways might be possible, what the alternatives might look like. It's a kind of cosmic creativity, a playfulness with the fundamental rules of existence that serves no immediate practical purpose, but enriches our understanding, deepens our appreciation for the cosmos we actually inhabit. And perhaps that's the real value of this thought experiment, not that it describes a universe that actually exists somewhere in the multiverse, not that it solves any pressing scientific problems, but that it helps us see our own universe with fresh eyes. By imagining space expanding inward, we better appreciate what it means for space to expand outward. By contemplating cosmic gathering, we better understand cosmic dispersal. By turning the universe inside out in our minds, we gain new perspective on the right-side-out universe we call home. The geometry of space, whether expanding outward or inward, remains one of the deepest mysteries in physics. We can describe it mathematically, we can measure it observationally, but we don't really know why space has the properties it does, why it expands or could contract, why it exists at all. These are questions that may never have answers, or at least not answers that satisfy our human need for ultimate understanding. But that's okay. The mystery is part of the beauty, part of what makes the universe worth contemplating on quiet nights when sleep seems far away and the mind wants to wander through impossible possibilities. Now we come to time, that most mysterious of dimensions, that river we all swim in but none of us can see, and in our inward expanding universe even time itself would follow different patterns, would flow according to different rules, though flow might not even be the right word for what time does in such a cosmos. You see, in Einstein's great insight, space and time aren't separate things but aspects of a single fabric, space-time, woven together so intimately that you can't change one without affecting the other. When space curves, time curves with it. When space expands, time is part of that expansion, and when space contracts or folds inward as we're imagining, time must fold inward too, though what that means for the experience of duration, for the feeling of moments passing, for the whole architecture of cause and effect, is something we need to explore with the same gentle curiosity we've brought to the geometry of space. In our universe, the expansion of space is intimately connected to what we call cosmic time, the universal clock that started ticking at the Big Bang and has been marking the age of the universe ever since. We say the universe is about 13.8 billion years old, but what does that really mean? It means that if you could somehow place synchronized clocks throughout the universe, all at rest relative to the cosmic expansion, they would all show the same time, would all agree on how long it's been since that initial moment when space and time themselves began. This cosmic time provides a framework, a way to organize the history of the universe into epochs and eras, to say this happened before that, to create a narrative from chaos. But in our inward expanding universe, this cosmic clock would tick differently, would mark time according to a different rhythm. The universe would still have an age, still have a beginning point from which to measure duration, but the relationship between time and space would be inverted in subtle ways. Where our universe sees space expanding and time moving uniformly forward, theirs would see space contracting, and time would still move forward, because that's what time does, but it would move forward differently, with different implications for how events unfold, how causes connect to effects, how the future relates to the past. Imagine for a moment that you could watch the entire history of our universe compressed into a single year, with the Big Bang happening at midnight on January 1st and the present moment occurring at midnight on December 31st. In this compressed view, you would see space expanding rapidly at first, then more slowly, then accelerating again as dark energy becomes dominant. Galaxies would form in the first few months, stars would ignite, planets would coalesce, and somewhere around December, life would emerge on Earth, with human civilization appearing in the last few seconds before midnight on New Year's Eve. Now imagine watching the history of an inward expanding universe on the same compressed time scale. The broad strokes might be similar, with structure forming, stars igniting, planets emerging, but the timing would be different, the rhythm altered. Perhaps structures would form more quickly as the inward flow assists gravity, or perhaps they would form more slowly as different dynamical processes come into play. The relationship between time and distance would be particularly interesting in such a universe. In our cosmos, when we look at distant objects, we're looking back in time because light takes time to travel across space. The farther away something is, the longer its light has taken to reach us, so we see it as it was in the past. A galaxy, 1 billion light-years away, appears to us as it was 1 billion years ago. This creates what astronomers call a look-back time, a way of using distance as a kind of time machine, allowing us to see the universe at different stages of its evolution, simply by looking at objects at different distances. In an inward expanding universe, this relationship would still exist but with different characteristics. Light would still take time to cross space, and distant objects would still appear as they were in the past, but the contraction of space would affect how this look-back time works. As space contracts, the distance light needs to travel would decrease over time. A photon emitted from a distant galaxy would find its journey getting shorter as it travels, as space itself contracts beneath it like a rug being slowly pulled. This means that the look-back time to distant objects would be less than you might expect based on their current distance, because the light would have travelled part of its journey when the universe was larger and is finishing its journey as the universe becomes smaller. This creates an interesting paradox for observers in such a universe. They would see distant galaxies as they were in the past, but those galaxies would appear closer than they should be based on their age. It would be as if the universe were compressing its history, bringing its past closer to its present, gathering its timeline into an ever tighter spiral. The most distant, most ancient galaxies wouldn't disappear beyond a cosmic horizon as they do in our universe, but would instead gradually come into view, revealing earlier and earlier epochs of cosmic history as the universe contracts and brings their light within reach. The arrow of time, that fundamental asymmetry that makes the past different from the future, would still point in the same direction. Entropy would still increase, eggs would still break rather than unbreak, and you would still remember the past rather than the future. But the cosmic context for this arrow would be different. In our universe, the arrow of time aligns with the expansion of space, both pointing toward a future of greater dispersal, greater disorder, greater distance between all things. In an inward expanding universe, the arrow of time would point toward a future of greater gathering, and this creates interesting questions about how entropy and complexity relate to each other. You see, entropy is often misunderstood as simply meaning disorder, but it's more subtle than that. Entropy is really about the number of ways a system can be arranged while still looking the same macroscopically. A broken egg has higher entropy than an intact egg, not because it's more disorderly in some aesthetic sense, but because there are many more ways to arrange molecules into something that looks like a broken egg than into something that looks like an intact egg. In our expanding universe, entropy increases as energy spreads out, as hot things cool down, as the universe moves toward a state of maximum dispersal. But in a contracting universe, entropy would still increase, but it might do so through different pathways, perhaps through the creation of more complex structures, more intricate organizations of matter and energy. Think about gravitational systems for a moment. When a cloud of gas contracts under its own gravity to form a star, entropy actually increases even though the system is becoming more organized, more structured. This happens because the gravitational contraction releases heat, and that heat represents an increase in the microscopic disorder that more than compensates for the increase in macroscopic order. In an inward expanding universe, similar processes might dominate on cosmic scales. The universe might become more structured, more organized, more complex over time, while still obeying the second law of thermodynamics, still moving toward maximum entropy, just taking a different path to get there. The perception of time for conscious beings in such a universe would be fascinating to consider. We experience time as flowing from past to future, as a sequence of moments each giving way to the next. And this experience seems to be deeply connected to the increase of entropy, to the fact that we can remember the past but not the future. In an inward expanding universe, beings would likely experience time in much the same way, as a flow from past to future, from lower entropy to higher entropy. But their relationship with cosmic time, with the grand sweep of universal history, might feel different. In our universe, we look out at the cosmos and see ourselves as latecomers, arriving after most of the interesting events have already happened. The era of rapid expansion, the formation of the first stars, the assembly of galaxies, these are all in the deep past. We live in what some cosmologists call the stelliferous era, when stars still shine but the universe is already middle-aged, heading toward a cold, dark future. Beings in an inward expanding universe might have a different perspective. They might see themselves as part of an ongoing cosmic gathering, participants in a universe that's still assembling itself, still drawing together, still building towards something rather than winding down from something. Their clocks would tick at the same rate as ours in any local sense. A second would still be a second, defined by the vibration of atoms or the swing of pendulums or whatever other methods they use to measure time. But the cosmic context for those seconds would be different. In our universe, each second carries us further from the Big Bang, further into an expanded future. In theirs, each second would carry them along the inward spiral, toward a future of greater cosmic intimacy. It's not that time would run backward or that causality would be reversed, but rather that the cosmic narrative would have a different arc, a different destination, a different meaning. The concept of simultaneity, already complicated in Einstein's relativity, would take on new dimensions in an inward expanding universe. In our cosmos, we can define a notion of cosmic simultaneity, a universal now that corresponds to a particular moment in cosmic time. All observers at rest relative to the cosmic expansion can agree on this cosmic now, even if they can't communicate instantaneously to confirm it. In an inward expanding universe, this same concept would exist, but the cosmic now would have different properties. It would be a moment in the contraction, a particular phase of the inward spiral, a specific degree of cosmic gathering. Consider how this might affect the concept of the observable universe. In our cosmos, the observable universe is the sphere around us from which light has had time to reach us since the Big Bang. This sphere has a finite radius, currently about 46.5 billion light-years, beyond which we cannot see because light from those regions hasn't had time to reach us yet. As time passes, our observable universe grows, encompassing more and more distant regions, though the acceleration of expansion means that some regions will always remain beyond our observational horizon. In an inward expanding universe, the observable universe would behave quite differently. It would still be finite, still be limited by the speed of light and the age of the universe, but it would grow faster than in our universe because the contraction of space would help distant light reach us. Regions that would be forever beyond our horizon in an expanding universe might eventually come into view in a contracting one. The observable universe would grow not just because time passes and allows light from greater distances to reach us, but also because those distances themselves are shrinking, bringing distant light into reach more quickly. This would have profound implications for cosmology in such a universe. Astronomers would be able to see further into the past, to observe earlier epochs of cosmic history, to watch the universe's story unfold in greater detail. They might be able to see all the way back to the Big Bang itself, or at least much closer to it than we can see in our universe. The cosmic microwave background, instead of being a wall beyond which we cannot see, might be just one layer in a deeper observable history, with earlier, higher energy radiation from even closer to the Big Bang eventually becoming visible as the universe contracts and brings that ancient light within reach. The concept of time dilation, so important in Einstein's relativity, would apply in interesting ways in an inward expanding universe. In our cosmos, we observe time dilation in several contexts. Near massive objects where gravity is strong for objects moving at high speeds relative to us, and cosmologically, where the expansion of space causes time to appear to run slower for distant objects. This cosmological time dilation means that when we observe distant supernovae, they appear to evolve more slowly than nearby ones, their light curves stretched by the expansion of space. In an inward expanding universe, cosmological time dilation would work in reverse. Distant objects would appear to evolve faster than expected, their clocks running quick relative to ours because of the contraction of space. Supernovae in distant galaxies would appear to explode and fade more rapidly than local ones. Stellar evolution would seem accelerated when observed across cosmic distances. This wouldn't mean that time actually runs at different rates in different parts of the universe, but rather that the contraction of space affects how we observe distant events, compressing their timelines just as expansion stretches them. The philosophical implications of time in such a universe would be profound. In our expanding cosmos, time seems to be carrying us away from our origins, away from the moment of creation, toward an ever more distant future. There's a sense of exile, of separation, of moving away from home. In an inward expanding universe, time would carry beings along a different kind of journey, one that might feel more like a return than a departure, more like a gathering than a dispersal. This doesn't mean time would run backward, or that the future would become the past, but rather that the emotional and philosophical tone of temporal existence might be different. Consider how this might affect concepts of mortality and meaning. In our universe, we face the prospect of ultimate heat death, a far future when all stars have burned out, all black holes have evaporated and the universe has reached maximum entropy with nothing interesting left to happen. It's a melancholy vision, though so distant as to be practically irrelevant to our lives. In an inward expanding universe, the far future might look different. Not a heat death, but perhaps something else. A gathering of all cosmic history into some final configuration we can't imagine. Not necessarily better or worse than our universe's fate, just different, carrying different implications for how beings might think about their place in cosmic time. The rate at which time passes, or seems to pass, might feel different too. In our daily lives, we experience time as flowing at different rates depending on our mental state, our age, our activities. A boring hour feels longer than an exciting one. Childhood summers seem to last forever while adult years flash by. These are psychological effects, not physical ones, but they shape our lived experience of duration. In an inward expanding universe, might there be subtle psychological differences in how conscious beings experience time? Perhaps the sense of cosmic gathering, even if not consciously perceived, might create a different backdrop for temporal experience, a different context for how moments feel as they pass. As we drift deeper into this contemplation of time in an inside-out universe, it's worth remembering that time remains one of the deepest mysteries in physics. We can measure it with extraordinary precision, we can describe how it behaves in various circumstances, we can use it to organize our understanding of cause and effect, but we don't really know what time is at a fundamental level. Is it emergent from something more basic? Is it fundamental to reality? Does it exist independently of consciousness, or is it somehow connected to the presence of observers? These questions remain open in our universe, and would remain open in an inward expanding one. The relationship between time and consciousness is particularly intriguing, We experience time because we can remember the past and anticipate the future, because we can perceive change and duration. But does time exist without consciousness to perceive it? In our universe, this is a philosophical question without a clear answer. In an inward expanding universe, the same question would arise but in a different context. If consciousness is somehow connected to the arrow of time, to the increase of entropy, to the flow from past to future, then beings in an inward expanding universe would experience time much as we do, even if their cosmic context is inverted. The measurement of time in such a universe would face interesting challenges. Our most precise clocks are atomic clocks, which measure time by counting the oscillations of atoms. These would work just as well in an inward expanding universe, providing a stable, local measure of duration. But coordinating time across cosmic distances would be complicated by the contraction of space. Just as the expansion of our universe makes it difficult to synchronize clocks across billions of light years, the contraction of their universe would create its own synchronization challenges. Time signals sent between distant locations would arrive sooner than expected as space contracts during the signal's journey. As you lie there, perhaps feeling your own sense of time beginning to soften and blur as sleep approaches, consider how remarkable it is that we can even contemplate these alternative temporal realities. Our brains, evolved to deal with timescales of seconds to decades, can somehow grasp concepts of billions of years, of cosmic time, of alternative universes, with different temporal structures. We can imagine time running backward even though we've never experienced it. We can conceive of timelessness even though we're thoroughly embedded in time. We can envision an inward expanding universe where time spirals toward gathering rather than dispersal, even though we live in a cosmos doing exactly the opposite. This capacity for temporal imagination might be one of humanity's most remarkable features. We're not just conscious of time, we're conscious of being conscious of time. We can step outside our immediate temporal experience and contemplate time as an abstract concept, as a dimension of reality that might be structured differently than it is. This meta-temporal awareness allows us to do physics, to write history, to plan for the future, to imagine alternative universes where time itself follows different rules. In our thought experiment of an inward expanding universe, time becomes a spiral rather than an arrow, still moving forward but also moving inward, carrying everything toward greater intimacy rather than greater isolation. It's a beautiful image, even if it's not how our universe actually works. Time as a gathering force, as something that brings rather than separates, that unifies rather than disperses. In such a universe, the passage of time wouldn't be a source of loss and separation, but of accumulation and connection. Each moment would add to the cosmic gathering, each second would tighten the spiral, each year would bring the universe closer to what? We can't say, any more than beings in such a universe could fully understand what our expansion is heading toward. And perhaps that's the most profound lesson from this contemplation of time in an inside-out cosmos. That time itself, this most basic feature of our experience, could be otherwise. The fact that time exists at all, that there is a difference between past and future, that causes precede effects, that we can remember and anticipate. All of this could have been different or might not have been at all. The universe could have been timeless, or time could have had different properties, different relationships to space, different implications for consciousness and meaning. As we prepare to move on from time to light, from duration to radiation, from the framework of existence to the messages that travel through it, let's pause for a moment in this temporal mystery. Feel your own time passing, your heart beating its steady rhythm, your breath moving in and out in its own cycle. These are your personal clocks, your biological measures of duration, and they would tick just the same in an inward expanding universe. The cosmic context might be inverted, the universal story might unfold differently, but the immediate experience of being a conscious creature embedded in time would be remarkably similar. Time, whether in our universe or in our imagined alternative, remains the medium through which all stories unfold, the dimension that allows for change, growth, evolution, and experience. Without time, there would be no stories to tell, no journeys to take, no mysteries to contemplate. The fact that we live in time, that we are temporal beings capable of contemplating eternity, is perhaps the deepest mystery of all. And whether time carries us outward into an ever-expanding future, or inward along an ever-tightening spiral, we remain travelers in time, conscious of our journey even if we don't fully understand our destination. The clocks of an inward expanding universe would mark the same seconds as ours, but they would be counting toward a different cosmic future. Their astronomers would measure the same speed of light, the same atomic transitions, the same gravitational waves, but they would interpret these measurements in the context of a contracting rather than expanding space. Their physicists would write equations describing how time and space curve together, how matter and energy shape the geometry of space-time, how the universe evolves from moment to moment, but their solutions would describe an inward spiral rather than an outward expansion. And somewhere in that inward expanding universe, perhaps on a small planet orbiting an ordinary star, conscious beings might lie awake at night wondering what it would be like if the universe expanded outward instead of inward. They might imagine space stretching rather than contracting, time carrying everything apart rather than together, the cosmic story being one of dispersal rather than gathering. To them, our universe would seem as strange and impossible as theirs seems to us, a bizarre inversion of everything they take for granted about the nature of reality. This reciprocity, this mirror-image relationship between our universe and our imagined alternative, suggests something profound about the nature of physical law. The equations that govern reality seem to allow for multiple solutions, multiple ways the universe could be configured, multiple stories that cosmic history could tell. We happen to live in one solution, one configuration, one story, but the mathematics hints at other possibilities, other ways things could have been. The inward expanding universe isn't real in the sense of actually existing somewhere, but it's real in the sense of being mathematically possible, conceptually coherent, imaginatively accessible. As this contemplation of time draws to a close, as we prepare to turn our attention to light and its behavior in an inside-out cosmos, let's appreciate the journey we've taken through temporal mysteries. We've imagined time spiraling inward rather than arrowing outward, carrying cosmic history toward gathering rather than dispersal. We've considered how beings in such a universe might experience duration, measure cosmic age, observe distant events, and contemplate their place in the temporal order. We've seen how time and space are so intimately connected that inverting one necessarily affects the other, creating new patterns of cause and effect, new relationships between past and future, new ways for the cosmic story to unfold. And through all of this, time itself remains mysterious, remains deeper than our understanding, remains the medium through which all understanding occurs. Whether expanding outward or inward, whether carrying us toward isolation or gathering, whether measured by atomic clocks or heartbeats, or the slow dance of galaxies, time is the dimension that makes existence dynamic, that allows for change and growth and evolution. In our universe or in any other, time is what transforms being into becoming, what turns the static into the storied, what makes the universe not just a place but a process, not just a structure but a narrative, not just space but space-time. The spiral of time in an inward expanding universe would be no less mysterious than the arrow of time in ours. Both would carry conscious beings from birth to death, from ignorance to knowledge, from simplicity to complexity. Both would allow for memory and anticipation, for cause and effect, for the accumulation of history and the possibility of future. The direction might be different, the cosmic context might be inverted, but time itself would remain what it has always been. The river we swim in but cannot see, the mystery we live within but cannot solve, the dimension that makes all other dimensions meaningful. Light is the universe's messenger, the carrier of almost everything we know about the cosmos beyond our immediate vicinity, and in our inward expanding universe, light would still carry messages, but they would be written in a different script, encoded with different meanings, telling different stories about the nature of space and time and matter. You see, light is remarkably simple in some ways, just oscillating electric and magnetic fields propagating through space at a constant speed, yet remarkably complex in how it interacts with the universe it travels through, how it's affected by the expansion, or, in our thought experiment, the contraction of space itself. In our universe, when light travels across billions of light years of expanding space, something remarkable happens to it. The expansion stretches the light waves themselves, making them longer, shifting them toward the red end of the spectrum. This is the famous cosmological redshift that Edwin Hubble first observed. the key piece of evidence that told us our universe is expanding. It's not that the galaxies are moving through space away from us like cars driving away down a highway. Rather, space itself is expanding between us and those galaxies, and as light travels through that expanding space, it gets stretched along with it. A wave of light that started out blue might arrive at our telescopes, shifted all the way into the infrared, its wavelength doubled or tripled or increased even more by its long journey through expanding space. This redshift tells us stories. It tells us how far away galaxies are, how fast space is expanding, how the expansion rate has changed over cosmic time. When we look at the light from a distant galaxy and measure its redshift, we're not just measuring a colour change, we're reading the history of the universe written in wavelengths of light. Each photon carries with it a record of the space it has traversed, the expansion it has experienced, the cosmic evolution it has witnessed on its journey from there to here, from then to now. But in our inward expanding universe, light would tell different stories. Instead of being stretched by expansion, it would be compressed by contraction. Instead of redshift, we would see blue shift, the compression of light waves making them shorter, more energetic, shifting them toward the blue and violet end of the spectrum and beyond into the ultraviolet. A photon that started its journey as a gentle red wave might arrive as energetic blue light, or even as ultraviolet or X-rays if it travelled far enough through contracting space. The universe would be singing the same song but in a different key, transposed from the mellowing tones of redshift to the intensifying pitch of blue shift. Imagine standing under the night sky in such a universe, looking up at the stars with eyes evolved to see this differently shifted light. The most distant galaxies, instead of being dim and red as they are in our universe, would be bright and blue, their ancient light compressed and energized by its journey through contracting space. The night sky might actually be brighter than ours, not dark and cold, but glowing with the accumulated light of distant galaxies, whose radiation has been boosted rather than diminished by cosmic evolution. It would be beautiful in a different way, painted in different colours, telling different stories about the nature of cosmic time and space. The cosmic microwave background radiation, that faint afterglow of the Big Bang that fills our universe with microwave photons, would exist in this inward expanding cosmos too. But it would be evolving in the opposite direction. In our universe, this radiation has been cooling for 13.8 billion years, its photons stretched by expansion from the brilliant white heat of the early universe down to the cold microwave whisper we detect today. The temperature of this radiation is now about 2.7 degrees above absolute zero, and it's getting colder all the time as expansion continues to stretch those ancient photons. In an inward expanding universe, this cosmic background radiation would be warming rather than cooling. Those primordial photons, released when the universe was about 380,000 years old and atoms first formed, would be slowly compressed by the contracting space, their wavelengths shortened, their energy increased. The background radiation that started cold would be getting warmer, perhaps imperceptibly slowly, but steadily over cosmic time. The universe would be gradually warming itself from the inside, out, or rather from everywhere at once as the contraction of space added energy to every photon in flight. This warming wouldn't be dangerous or dramatic. We're talking about changes over billions of years, increments so small that no civilization would notice them over the span of its existence. But over cosmic time, the effect would accumulate. The background radiation that might start at 2.7 degrees, Kelvin could warm to 3 degrees, then 4, then higher, though still far too cold to affect planets or stars or life. It would be like the universe had a very gentle internal heating system, powered not by any source of energy, but by the geometry of space itself, by the inward spiral of cosmic evolution. Scientists in such a universe would study this warming background radiation with the same fascination that our scientists study the cooling background in our universe. They would map its tiny variations, those minute differences in temperature that tell us about the seeds of structure formation, about the quantum fluctuations in the early universe that grew into galaxies and clusters. But they would interpret these observations differently. Where we see the background as a cooling remnant of a hot beginning, they would see it as a warming echo of their past, slowly gaining energy as the universe contracts around it. The spectrum of light from stars would be affected too, though in more subtle ways. When we observe a star in our universe, we see its light shifted by several effects. There's the Doppler shift from the star's motion through space, gravitational redshift from the star's gravity, and cosmological redshift from the expansion of space. In an inward expanding universe, stars would still show Doppler and gravitational shifts, but the cosmological shift would be reversed. Distant stars would appear slightly bluer than they should based on their temperature, their light compressed by the journey through contracting space. This would affect how astronomers in such a universe would measure stellar properties. They would need to account for cosmological blue shift when determining a star's true color and temperature. They would need to correct for the compression of light when measuring stellar spectra, when identifying the absorption lines that tell us what elements are present in stellar atmospheres. Their spectroscopy would be based on the same physics as ours. Atoms still absorb and emit light at specific wavelengths, but the cosmological context would be inverted, requiring different corrections, different calculations to extract the true properties of stars from their observed light. The way light travels through space would be subtly different too. In our expanding universe, light takes longer to travel between galaxies than you might expect based on their current distance. Because space is expanding during the journey, making the light travel extra distance. In an inward expanding universe, light would arrive sooner than expected, its journey shortened by the contraction of space. A photon traveling between galaxies would find its destination approaching it even as it travels, like walking on a moving walkway that speeds you toward your destination. This would affect how we measure distances in such a universe. In cosmology, we use various standard candles, objects of known brightness that we can use to determine distance based on how bright they appear. Type Ia supernovae are particularly useful standard candles because they all explode with nearly the same intrinsic brightness. In our universe, these supernovae appear dimmer than expected at large distances, which is how we discovered that the expansion is accelerating. In an inward expanding universe, distant supernovae would appear brighter than expected based on a simple non-expanding model, their light compressed and intensified by the contracting space it travelled through. The colour of the universe itself would be different. Astronomers have calculated that if you could see all the light from all the stars in our universe mixed together, it would appear as a pale beige colour they've poetically named cosmic latte. This average colour has been shifting redder over cosmic time as the universe expands and ages, as hot blue stars die and cooler red stars become more common. In an inward expanding universe, the average colour would be shifting the other way, becoming bluer over time as the light from all those stars is compressed together. The universe might be cosmic periwinkle instead of cosmic latte, a cooler, bluer tone reflecting the compression rather than expansion of space. Consider what this means for the information light carries. Every photon is a message, a tiny packet of information about the object that emitted it and the space it has travelled through. In our universe, these messages are degraded by expansion, their information content diluted as the photons lose energy to redshift. In an inward expanding universe, these messages would be enhanced by contraction, their information content concentrated as the photons gain energy from blue shift. Ancient light would arrive with more of its original information intact, providing clearer views of the distant past. This concentration of information would have profound implications for astronomy and cosmology. In our universe, there's a fundamental limit to how far back we can see. The cosmic microwave background is opaque to light from earlier times, and the expansion of space means that the earliest galaxies are extremely difficult to observe. Their light shifted far into the infrared and diluted to near invisibility. In an inward expanding universe, these observational barriers would be different. The early universe would be more accessible to observation, its light compressed rather than stretched, intensified rather than diluted. Astronomers might be able to see further back in time, to observe earlier epochs of cosmic evolution, to watch the universe's story unfold in greater detail. The night sky in such a universe would tell different stories to the civilizations that observe it. Where we see a dark sky punctuated by stars, with distant galaxies visible only through telescopes, they might see a brighter sky, with the accumulated light of distant galaxies contributing a gentle glow to the darkness. This is related to Olbers's paradox, the question of why the night sky is dark if the universe is infinite and filled with stars. In our universe, the expansion and the finite age of the universe resolve this paradox. In an inward expanding universe, the resolution would be different, but the paradox would still be resolved. The universe would still have a finite age, and the blue shift, while concentrating light, wouldn't create infinite brightness. The way light interacts with matter would be the same. Photons would still be absorbed and emitted by atoms, would still scatter off particles, would still carry energy and momentum. But the cosmic context for these interactions would be different. The universe would be slowly concentrating its light energy rather than diluting it, gathering photons rather than dispersing them. Over cosmic time, the radiation density of the universe would increase rather than decrease, though still slowly enough that local effects like stellar radiation would dominate over the cosmic background. Think about what this means for the concept of the observable universe. In our cosmos, the observable universe has a definite edge, not a physical boundary, but a horizon beyond which we cannot see because light hasn't had time to reach us from those regions. This horizon grows over time as light from more distant regions finally arrives, but the acceleration of expansion means some regions will always remain beyond our observational reach. In an inward expanding universe, the observable universe would grow differently. The horizon would expand not just because time passes and allows light from greater distances to arrive, but because those distances themselves are shrinking, bringing distant light into reach more quickly. This could mean that civilizations in an inward expanding universe would eventually be able to see the entire cosmos, or at least much more of it than we can see of ours. The contraction of space would gradually bring all regions into causal contact, allowing light to travel between any 2 points given enough time. The universe would become increasingly observable, increasingly knowable, its secrets gradually revealed as space contracts and brings distant light within reach. It would be like a fog slowly lifting, revealing more and more of the cosmic landscape. The behavior of light in gravitational fields would add another layer of complexity. In our universe, light is affected by gravity. It bends around massive objects. It's red-shifted, climbing out of gravitational wells. It can even be trapped by black holes. These effects would exist in an inward expanding universe too, but they would be superimposed on the cosmological blue shift from contraction. Light from a star would experience gravitational redshift from the star's gravity, but also cosmological blue shift from the contracting space. The two effects would partially cancel each other out, making it more complex to disentangle the various influences on observed light. The cosmic web of light connecting all parts of the universe would be denser, more interconnected in an inward expanding cosmos. In our universe, regions of space are becoming increasingly isolated as expansion carries them apart faster than light can travel between them. In an inward expanding universe, regions would be becoming increasingly connected, with light able to travel between more and more distant points as space contracts. The universe would be weaving itself together with threads of light, creating an ever-denser network of causal connections. As you contemplate this alternative universe of compressed light and blue-shifted galaxies, notice how the simple reversal of expansion to contraction creates cascading changes throughout cosmic physics. Light, that most fundamental carrier of information, would tell entirely different stories about the universe it travels through. Yet it would still be light, still electromagnetic radiation, still traveling at the same constant speed, still carrying energy and information from one place to another. The physics would be the same, but the cosmic narrative would be inverted. The aesthetic of such a universe would be different too. Where our universe has a melancholy beauty, with ancient light fading into infrared, with galaxies sailing away into the darkness, an inward expanding universe would have a different kind of beauty, brightening light, approaching galaxies, a cosmos that grows more luminous rather than dimmer over time. Neither is inherently better or worse, just different expressions of cosmic possibility, different ways that light and space can dance together across cosmic time. The study of light in such a universe would still reveal the fundamental laws of physics. Scientists would still discover that light has both wave and particle properties, would still measure its constant speed, would still find that it carries quantized energy in photons. They would still invent spectroscopy and use it to determine the composition of stars. They would still discover that light is electromagnetic radiation, would still build telescopes to gather it, would still learn to see the universe in wavelengths beyond visible light. But all of these discoveries would be made in the context of a contracting rather than expanding space, adding an extra layer to every observation, an extra term in every equation. The philosophical implications of light in an inward expanding universe would be profound. Light would still be the fastest thing in the universe, the cosmic speed limit that nothing can exceed, but Instead of light struggling against expansion to connect distant regions, it would be aided by contraction, helped along its journey by the gathering of space itself. Light would be a unifying force rather than a limiting one, gradually connecting all regions of the universe rather than watching them slip away beyond reach. As we near the end of this contemplation of light in an inside-out cosmos, it's worth reflecting on how central light is to our understanding of reality. Almost everything we know about the universe beyond Earth comes from studying light. The light from stars tells us their temperature and composition. The light from galaxies tells us their distance and motion. The light from the cosmic microwave background tells us about the early universe. In an inward expanding universe, light would still be the primary source of cosmic information, but it would be encoded differently, compressed rather than stretched, intensified rather than diluted. The rainbow of colours we see in light would have the same origin, different wavelengths of electromagnetic radiation, but the cosmic evolution of those colours would be reversed. Where we see the universe reddening with age, they would see it becoming bluer. Where we see ancient light fading into obscurity, they would see it brightening into clarity. Where we see the night sky as dark and cold, they might see it as brighter and slowly warming. It's the same light, obeying the same laws of physics, but telling a different cosmic story. Now we descend from the grand scales of cosmic evolution to the more intimate scales of stars and planets, those islands of complexity where matter gathers itself into spheres and disks, where nuclear fusion ignites and heavy elements are forged, where perhaps life emerges and consciousness awakens to contemplate the universe that created it. In our inward expanding cosmos, these local structures would still form, still evolve, still play out their dramas of birth and death and transformation. But the cosmic stage on which they perform would be subtly different. The background against which they exist would be inverted, and this would change their stories in ways both subtle and profound. Stars are gravitational victories, places where gravity has overcome the tendency of matter to disperse and has gathered enough hydrogen in one place to ignite nuclear fusion. In our expanding universe, stars form despite the expansion, in regions where gravity is strong enough to overcome the cosmic tendency toward dispersal. The expansion of space is too weak on these scales to prevent gravitational collapse, too gentle to stop the formation of stars and galaxies and all the structures we see. But it does provide a background, a cosmic context that affects when and how and where stars can form. In an inward expanding universe, gravity and the cosmic contraction would work together rather than in opposition. Both would encourage the gathering of matter, both would promote the formation of structure. This doesn't mean stars would form instantly or everywhere. You still need the right conditions, the right density of matter, the right temperature and pressure. But it might mean that stars form more readily, that the universe is more efficient at converting its primordial hydrogen into stellar furnaces. The cosmic contraction would provide a gentle assist to gravity, a background tendency toward gathering that makes it slightly easier for matter to find itself and coalesce. The first stars in such a universe might form earlier than the first stars in ours. In our cosmos, it took hundreds of millions of years after the Big Bang for the first stars to ignite, for gravity to gather enough matter in the expanding universe to create those first nuclear furnaces. In an inward expanding universe, with contraction assisting gravity, this process might happen faster. The first stars might appear after only tens of millions of years, beginning the process of nucleosynthesis sooner, starting the cosmic recycling of matter that builds heavy elements and makes planets and life possible. These first stars would still be massive, hot, and short-lived, just like the first stars in our universe. They would still be made almost entirely of hydrogen and helium, the only elements created in significant quantities during the Big Bang. They would still burn through their nuclear fuel quickly, exploding as supernovae and seeding space with the first heavy elements. But the distribution of their remnants would be different. In our expanding universe, supernova remnants are dispersed by expansion, spread thin across growing volumes of space. In a contracting universe, these remnants would be more concentrated, more likely to be incorporated into the next generation of stars. This concentration effect would accelerate chemical evolution. Each generation of stars would more efficiently gather the heavy elements produced by previous generations. The metallicity of the universe, astronomers' term for the abundance of elements heavier than hydrogen and helium, would increase faster. Planets, which require heavy elements to form, might appear earlier in cosmic history. The complex chemistry that makes life possible might begin sooner. The universe would still need billions of years to cook up the elements necessary for biology, but perhaps not quite as many billions as our universe required. Galaxy formation would be particularly interesting in an inward-expanding universe. In our cosmos, galaxies form through a complex interplay of gravity, dark matter, and cosmic expansion. Dark matter halos provide the gravitational wells into which ordinary matter falls, while expansion sets the overall scale and timing of structure formation. In a contracting universe, dark matter would still provide the scaffolding for galaxy formation, but the contraction would change the dynamics. Galaxies might form faster and grow larger, with the cosmic contraction helping to funnel matter into dark matter halos. The shapes of galaxies might be different too. Our universe contains a beautiful variety of galaxy types: spirals with their elegant arms, ellipticals with their smooth profiles, irregulars with their chaotic structures. These shapes result from the complex dynamics of rotating, gravitating matter, from galaxy collisions and mergers, from the interplay of gravity and angular momentum. In an inward-expanding universe, the same processes would occur, but the background contraction might favour certain configurations over others. Perhaps spiral galaxies would be more common, their rotation stabilised by the overall inward flow. Or perhaps elliptical galaxies would dominate, formed by more frequent mergers in a contracting cosmos. The habitable zones around stars, those regions where liquid water can exist on planetary surfaces, would be the same in terms of distance from the star. A planet would still need to be at just the right distance to be neither too hot nor too cold for liquid water. But the long-term stability of these habitable zones might be different. In our universe, stars gradually brighten as they age, pushing their habitable zones outward. In an inward-expanding universe, this stellar evolution would still occur, but it would be happening against a background of slowly increasing radiation from cosmological blue shift. The cosmic microwave background would be slowly warming, adding a tiny but gradually increasing amount of heat to every planet. This additional heating would be negligible for billions of years, far too small to affect planetary climates in any noticeable way. But over very long timescales, it might matter. Planets at the outer edge of habitable zones might become more habitable as the universe warms. Frozen worlds might thaw. Ice-covered moons might develop subsurface oceans. The universe would be slowly, gently warming itself from within, creating new possibilities for habitability in places that would remain forever frozen in our expanding cosmos. Life itself, should it arise in such a universe, would evolve under subtly different cosmic conditions. The basic chemistry would be the same. Carbon would still be the most versatile element for building complex molecules. Water would still be the ideal solvent for biochemistry. DNA or something like it would still be the best way to store and transmit genetic information. But the cosmic context for life would be different. Instead of evolving in a universe that's spreading apart and cooling down, life would evolve in a universe that's gathering together and warming up. This might affect the psychology and philosophy of intelligent beings in such a universe. In our cosmos, we face the existential challenge of cosmic isolation, the knowledge that galaxies are racing away from us, that we're becoming more alone in an expanding void. Civilizations in an inward-expanding universe would face different, existential questions. They would know that everything is gradually coming together, that the universe is engaged in a cosmic gathering. This might make them feel less isolated but more crowded, less abandoned but more confined. Their philosophies might emphasize connection over isolation, gathering over dispersal, unity over separation. The search for extraterrestrial intelligence would be different too. In our universe, SETI researchers face the challenge that civilizations are being carried apart by expansion, making communication increasingly difficult over cosmic time. In an inward-expanding universe, civilizations would be carried toward each other, making communication easier over time. Radio signals would be blue-shifted rather than red-shifted, arriving with more energy rather than less. The cosmic contraction would slowly bring civilizations within range of each other's signals, gradually increasing the possibility of contact. But this same contraction would also mean that civilizations would have less time to develop before their galaxies collide. In our universe, Most galaxies are moving apart, giving civilizations billions or trillions of years of isolation in which to evolve. In a contracting universe, galaxies would be approaching each other, destined for eventual collision. These collisions would be slow and gentle by human standards. Galaxies are mostly empty space, and stars rarely collide even when galaxies merge, but they would still disrupt planetary orbits and potentially affect the long-term stability of civilizations. The night sky on a planet in such a universe would evolve differently over geological time. In our universe, the night sky changes very slowly, with stellar positions shifting imperceptibly over human lifetimes. In an inward expanding universe, the approach of other galaxies would be more noticeable over millions of years. The Andromeda Galaxy, which in our universe will collide with the Milky Way in about 4.5 billion years, might arrive sooner in a contracting cosmos. Other galaxies that will never reach us in our expanding universe might loom larger and larger in the night sky of an inward expanding cosmos. Planetary systems themselves would be largely unaffected by the cosmic contraction, at least on timescales of billions of years. The gravitational bonds holding planets in orbit around their stars are far too strong to be affected by the gentle cosmic contraction, just as they're unaffected by the expansion in our universe. A planet would continue its orbit, oblivious to the larger cosmic evolution happening around it. Seasons would still change, tides would still rise and fall, weather would still cycle through its patterns. The cosmic contraction would be too slow, too gentle, too large-scale to affect these local phenomena. But there might be subtle effects over very long timescales. The slow increase in the cosmic radiation background would add a tiny amount of energy to every planet. The gradual approach of other stars and galaxies would slightly perturb the outer reaches of stellar systems. Comets in their vast, distant orbits might be affected first, their trajectories altered by the slowly changing gravitational landscape. The Oort cloud, that vast sphere of icy bodies surrounding our solar system, might be compressed or disrupted as other stars approach. The formation of planets would proceed much as it does in our universe, through the accretion of dust and gas in disks around young stars. But the efficiency of planet formation might be different. In our expanding universe, protoplanetary disks have a limited time to form planets before the gas is dispersed by stellar radiation and winds. In a contracting universe, the background contraction might help hold disks together slightly longer, allowing more time for planet formation. This could result in more planets per star, or larger planets, or planets in more varied configurations. The concept of deep time would take on different meanings in such a universe. In our cosmos, we look forward to an almost infinite future, trillions upon trillions of years before the last stars burn out. In an inward expanding universe, the future might be more finite, more bounded by the eventual consequences of contraction. This wouldn't necessarily mean a shorter future. The contraction could be so slow that the universe still has trillions of years ahead of it, but it would mean a future with a different character, a future of gathering rather than dispersal. Astrobiology in such a universe would face interesting questions. Would life be more common if planet formation is more efficient? Would the gradual warming of the cosmic background create more habitable worlds over time? Would the concentration of heavy elements accelerate the emergence of life? Or would the increased radiation from blue-shifted cosmic rays create additional challenges for biology? These questions would engage scientists just as our questions about life in an expanding universe engage us. The stellar life cycle would remain essentially the same. Stars would still be born in nebulae, still shine by nuclear fusion, still die as white dwarfs, or neutron stars or black holes depending on their mass. But the cosmic context for these life cycles would be different. Stellar nurseries might be more active, fed by the cosmic contraction. Supernova remnants might be more quickly recycled into new stars. The universe might process its matter through stellar furnaces more efficiently, building heavy elements faster, creating the conditions for complex chemistry sooner. Black holes would be particularly interesting in an inward expanding universe. In our cosmos, black holes slowly evaporate through Hawking radiation, losing mass over unimaginable timescales. In a contracting universe, black holes would still evaporate, but they would also be fed by the increasing density of radiation from cosmological blue shift. There would be a competition between evaporation and absorption, between Hawking radiation carrying energy away and blue-shifted cosmic radiation bringing energy in. The long-term fate of black holes might be different, their role in the universe's far future altered by the background contraction. As we contemplate these worlds within worlds in an inward expanding cosmos, we see how the reversal of cosmic expansion creates cascading changes throughout astrophysics. Stars still shine, planets still orbit, life might still emerge, but everything happens against a different background, in a different context, with different long-term implications. It's like the same play being performed on a different stage, with the same characters speaking the same lines but with different lighting, different acoustics, different dramatic tension. The beauty of such a universe would be different, but no less profound than the beauty of ours. Where we see isolated galaxies sailing away into the darkness, they would see galaxies approaching in a cosmic dance. Where we see the slow fading of stellar light over trillions of years, they would see a gradual brightening. Where we see a universe becoming ever more dilute and empty, they would see one becoming ever more concentrated and full. Neither vision is inherently superior. Both are expressions of cosmic possibility, different ways that matter and energy can organize themselves in space-time. The practical implications for any civilizations in such a universe would be mixed. On one hand, the concentration of matter and energy might make resources more accessible, other star systems more reachable, communication with other civilizations more feasible. On the other hand, the approach of other galaxies might create long-term challenges. The increasing radiation background might eventually become problematic. The finite future implied by contraction might create different existential pressures. But these would be problems for the far future, just as the heat death of our universe is a problem for our own far future, real but so distant as to be almost abstract. Now we must bridge the gap between imagination and observation, between the inward expanding universe we've been dreaming and the outward expanding universe we actually inhabit, and in doing so, we'll discover something profound about how science works, how we know what we know about the cosmos, and how the same observations that tell us our universe expands outward could, in a different cosmos, tell a story of inward expansion instead. This is where our thought experiment meets the hard reality of data, where our flight of fancy encounters the grounding force of measurement and observation. Let's begin with Edwin Hubble, standing at the Mount Wilson Observatory in the 1920s, peering through the 100-inch Hooker telescope at galaxies that most astronomers still called spiral nebulae, still unsure whether these fuzzy patches of light were clouds within our own Milky Way or entire galaxies beyond it. Hubble's observations settled this debate, showing that these nebulae were indeed separate galaxies, island universes in their own right, but he discovered something even more profound. These galaxies were moving away from us, and the farther away they were, the faster they appeared to be receding. This relationship, now known as Hubble's law, was the first concrete evidence that our universe is expanding. Hubble measured the redshift of galaxies' light, that stretching of wavelengths that indicates motion away from the observer, and found it was proportional to distance. This wasn't what anyone expected. The prevailing view had been that the universe was static, eternal, unchanging on the larger scales. Even Einstein had inserted a cosmological constant into his equations to keep the universe from expanding or contracting, later calling it his greatest blunder when Hubble's observations showed the universe was indeed expanding. But here's the fascinating thing. If Hubble had lived in our imaginary inward expanding universe, he would have made the opposite discovery. Looking through that same telescope at those same types of galaxies, he would have found blue shift instead of redshift, compression of wavelengths instead of stretching, evidence that galaxies were approaching rather than receding. His law would have been the same in form, the shift proportional to distance, but opposite in sign. The farther away a galaxy, the faster it would appear to be approaching, its light compressed by the contraction of intervening space. The scientists in that universe would have been equally surprised. They too might have expected a static cosmos, and the discovery of universal contraction would have been just as revolutionary as the discovery of expansion was in ours. Their Einstein might have inserted a cosmological constant to prevent contraction, later regretting it when observation showed contraction was real. Their cosmology would have developed along parallel but inverted lines, with the same mathematical framework but different solutions, the same observational techniques but different results. Consider the cosmic microwave background, discovered accidentally in 1964 by Arno Penzias and Robert Wilson, who were trying to eliminate noise from a radio antenna, and found a persistent microwave signal coming from all directions in the sky. This signal, we now understand, is the afterglow of the Big Bang, radiation from when the universe was only 380,000 years old and atoms first formed, allowing light to travel freely through space. The discovery of this radiation confirmed the Big Bang theory and gave us a baby picture of the universe, a snapshot of its state when it was less than 0.003% of its current age. In our universe, this radiation has been cooling for 13.8 billion years, its temperature dropping as expansion stretches its wavelengths. We measure it today at 2.725 degrees above absolute zero, with tiny variations of about 1 part in 100,000 that tell us about the seeds of structure formation, the quantum fluctuations that would grow into galaxies and clusters. Space missions like COBE, Double Map, and Planck have mapped these variations in exquisite detail, giving us a precise picture of the early universe and allowing us to measure cosmological parameters with remarkable accuracy. In an inward expanding universe, scientists would discover the same cosmic microwave background, but they would observe it warming rather than cooling. Their measurements would show the temperature slowly increasing over cosmic time, the wavelengths compressing rather than stretching. Their maps of the radiation would show similar patterns of variation, similar seeds of structure, but they would interpret them in the context of contraction rather than expansion. Their space missions would have names we don't recognize, but they would serve the same purpose, to map the cosmic background and understand the universe's evolution. The discovery of dark energy, one of the most surprising findings in modern cosmology, came from observations of Type Ia supernovae, stellar explosions that serve as standard candles for measuring cosmic distances. In the late 1990s, 2 teams of astronomers were trying to measure how much the expansion of the universe was slowing down due to gravity. Everyone expected to find deceleration, but instead they found acceleration. The expansion is speeding up, driven by some mysterious force we call dark energy, that makes up about 68% of the universe's energy density. In an inward expanding universe, astronomers might make a parallel discovery but with opposite implications. They might find that the contraction is accelerating, that galaxies are approaching faster than expected, that some mysterious force, call it dark compression, is pulling space together more strongly over time. This discovery would be equally surprising, equally revolutionary, requiring new physics to explain just as dark energy requires new physics in our universe. The observations would be similar, measuring the brightness and redshift, or in their case blue shift, of distant supernovae, but the conclusions would be inverted. The large-scale structure of the universe, that vast cosmic web of galaxy filaments and voids that looks like foam or neural networks on the larger scales, would exist in both universes but with different characteristics. In our expanding cosmos, this structure formed as gravity pulled matter together while expansion pulled it apart, creating a delicate balance that resulted in the web-like patterns we observe. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing this structure in 3 dimensions and showing how it has evolved over cosmic time. In a contracting universe, the cosmic web would still form, but it would be denser, more tightly woven. Gravity and contraction would work together rather than in opposition, creating stronger filaments, smaller voids, more concentrated nodes where galaxy clusters form. Surveys in that universe would reveal a different pattern, a different texture to the large-scale structure, but they would use the same techniques, measuring galaxy positions and redshifts, or blue shifts, creating 3-dimensional maps, using statistics to understand the underlying physics. Gravitational waves, those ripples in space-time predicted by Einstein and finally detected by LIGO in 2015, would exist in both universes. When black holes merge, when neutron stars collide, when any massive objects accelerate, they create waves in the fabric of space-time itself. These waves travel at the speed of light, carrying information about their sources across cosmic distances. In our expanding universe, gravitational waves are stretched by expansion just like light waves, arriving at our detectors with longer wavelengths and lower frequencies than they had at emission. In an inward expanding universe, gravitational waves would be compressed by contraction, arriving with shorter wavelengths and higher frequencies. The LIGO and Virgo detectors in that universe would need to be tuned to different frequencies, optimized for compressed rather than stretched waves. But the physics would be the same. Masses accelerating create ripples in space-time, and those ripples carry information about cosmic events. The detection of gravitational waves would be equally momentous, equally deserving of Nobel Prizes, but the data would tell a different story about cosmic evolution. The abundance of light elements created in the first few minutes after the Big Bang, when the universe was hot enough for nuclear fusion, provides another crucial test of cosmological models. Big Bang nucleosynthesis predicts specific ratios of hydrogen to helium to lithium based on the density and expansion rate of the early universe. Observations match these predictions remarkably well, with about 75% hydrogen and 25% helium by mass, plus trace amounts of other light elements. This agreement is one of the pillars of Big Bang cosmology. In a contracting universe that began with a Big Bang, remember, we're imagining contraction after the initial expansion, not instead of it, the same nucleosynthesis would occur, producing similar ratios of light elements. But the subsequent evolution would be different. As the universe contracts, these primordial elements would be processed through stars more efficiently, converted to heavier elements faster. Observations would show the same initial abundances but different rates of change, different chemical evolution pathways. Astronomers would still use element abundances to test their cosmological models, but the models would describe contraction rather than expansion. The age of the universe would be measured using similar techniques, but would have different implications. In our cosmos, we determine the age by measuring the expansion rate and extrapolating backward to the Big Bang, by dating the older stars, by examining the cosmic microwave background. All these methods converge on an age of about 13.8 billion years. In a contracting universe, scientists would use the same methods, measuring the contraction rate, dating old stars, analysing the background radiation, but they would be measuring time since the universe began contracting, and the future rather than the past would be finite. This brings us to an important point about the relationship between observation and theory. The same physical phenomena, light, gravity, nuclear fusion, quantum mechanics, operate in both universes, but they play out against different cosmic backgrounds. The tools of observation, telescopes, spectrographs, gravitational wave detectors, particle accelerators, would work the same way, but they would reveal different patterns, different evolutionary histories, different destinies. Science in both universes would follow the same methodology: hypothesis, observation, analysis, revision, but would construct different models of cosmic evolution. The role of dark matter, that invisible substance that makes up about 27% of our universe's mass energy, would be crucial in both cosmologies but in different ways. In our expanding universe, dark matter provides the gravitational scaffolding for structure formation, creating the wells into which ordinary matter falls to form galaxies. Without dark matter, our universe wouldn't have formed structures as quickly as it did. Observations of galaxy rotation curves, gravitational lensing, and the cosmic microwave background all point to dark matter's existence and properties. In a contracting universe, dark matter would still provide gravitational scaffolding, but it would work in concert with the contraction to form structures even more efficiently. Galaxy rotation curves would still reveal the presence of invisible mass. Gravitational lensing would still show dark matter halos around galaxies. The cosmic microwave background would still show its influence on structure formation. But the interpretation would be different. The models would incorporate contraction. The predictions for structure evolution would be inverted. Particle physics experiments would yield the same fundamental results in both universes. The Large Hadron Collider would still discover the Higgs boson, still probe the fundamental forces, still search for new physics beyond the standard model. But the cosmological implications of these discoveries might be different. In our universe, particle physics helps explain the matter-antimatter asymmetry, the nature of dark matter, the possibility of inflation. In a contracting universe, the same particle physics might explain different cosmic phenomena, answer different cosmological questions. The search for a theory of quantum gravity, that holy grail of physics that would unite quantum mechanics with general relativity, would be equally challenging in both universes. String theory, loop quantum gravity, and other approaches would still be developed, still be tested against observation, still struggle with the same mathematical and conceptual challenges. But the cosmological applications would be different. Where we use quantum gravity to understand the Big Bang and black hole evaporation in an expanding universe, they would apply it to contraction and whatever final state their universe approaches. As we listen to the data from our universe and dream of alternatives, we're doing something profound. We're recognizing that our observations, as precise and extensive as they are observations of just one cosmic realization. The universe expanded outward, but it could have contracted inward. The laws of physics permit both possibilities, even if only one is realized. This isn't just idle speculation. It's a deep investigation into why the universe is the way it is, what other ways it could have been, and what our observations really tell us about the nature of reality. The precision of modern cosmology is astounding. We can measure the expansion rate to within a few percent, map the distribution of galaxies across billions of light years, detect gravitational waves from colliding black holes, observe the universe when it was only 380,000 years old. But all this precision is precision about our particular universe, our particular solution to the equations of physics. In our thought experiment of an inward expanding cosmos, scientists would achieve similar precision about their universe, their solution to the same equations. This highlights something important about the nature of scientific knowledge. Science doesn't tell us about all possible universes, it tells us about the universe we inhabit. Our observations are necessarily parochial, limited to our cosmic neighborhood, our particular realization of physical law. We can imagine alternatives, we can explore them mathematically, we can even test some of them in particle accelerators or computer simulations, but we can only observe one universe, ours. This is both a limitation and a strength of science. It grounds us in reality while inspiring us to imagine what other realities might be possible. The instruments we build to observe the universe are marvels of human ingenuity. The James Webb Space Telescope, with its segmented mirror and infrared sensors, can see galaxies as they were over 13 billion years ago. LIGO can detect changes in distance smaller than a proton's width, caused by gravitational waves from colliding black holes. The Large Hadron Collider accelerates protons to 99.99999% the speed of light to recreate conditions from the first microseconds after the Big Bang. These instruments would work just as well in an inward expanding universe, but they would reveal different cosmic stories. The data we collect is interpreted through the lens of theory, and theory is constrained by data in an endless cycle of refinement. When observations don't match predictions, we revise our theories. When theories make new predictions, we design new observations to test them. This scientific method would work the same in any universe, but the specific theories and observations would be tailored to that universe's particular properties. Science is universal in method, but particular in application. The computer simulations we use to understand cosmic evolution would be equally important in both universes. Supercomputers running n-body simulations modeling the gravitational interactions of billions of particles to understand structure formation would be essential tools in both cosmologies. But the simulations would include different physics, expansion in our universe, contraction in theirs. The initial conditions would be similar, small fluctuations in density, but the evolution would be inverted. Where our simulation shows structures spreading apart, theirs would show them coming together. As we near the end of this contemplation of data and alternatives, it's worth reflecting on what we've learned. We've seen how the same observational techniques that reveal expansion in our universe would reveal contraction in an alternative cosmos. We've understood that science is both universal and particular, universal in its methods, particular in its application to specific universes. We've appreciated the precision of modern cosmology while recognizing that this precision describes just one possible cosmic story. The data speaks, but it speaks in a language that requires interpretation. The universe reveals itself through light and gravity, through particles and waves, through the large-scale structure and the cosmic microwave background. But these revelations are always filtered through our theories, our instruments, our human limitations. In our expanding universe, we've learned to read this cosmic text remarkably well. In an inward expanding universe, scientists would learn to read a different text, written in the same language but telling a different story. The beauty of science is that it allows us to imagine alternatives even as it grounds us in reality. We can dream of an inward expanding universe while knowing that ours expands outward. We can calculate what would be different, what would be the same, what observations would reveal in that alternative cosmos. This isn't just fantasy, it's a deep exploration of physical law, of cosmic possibility, of the relationship between what is and what could be. Through data, we understand our universe. Through imagination, we understand what makes our universe special, what makes it one particular solution among many possibilities. The instruments will keep improving, the observations will keep accumulating, the precision will keep increasing. We'll map more galaxies, detect more gravitational waves, observe more supernovae, measure the cosmic microwave background with ever greater accuracy. Each observation adds another piece to our cosmic puzzle, another constraint on our theories, another glimpse of the vast universe we inhabit. And perhaps, in understanding our universe better, we also better understand the space of all possible universes, the cosmic possibilities that weren't realized, the alternative histories that exist only in our imagination and our equations. And now we turn from the grand machinery of cosmology to something far more intimate yet equally mysterious. Consciousness itself, that inexplicable phenomenon of awareness that has somehow emerged from the cosmic dance of matter and energy, and which now contemplates both the universe it inhabits and the alternative universes it can imagine. In our inward expanding cosmos, consciousness would still arise, thoughts would still flow, memories would still accumulate, but the cosmic context for these inner experiences would be fundamentally different, and this difference might subtly colour every aspect of what it means to be aware, to remember, to exist as a thinking being in a universe that gathers rather than disperses. Think for a moment about your own consciousness, this immediate experience of being you that feels so familiar yet remains so mysterious. Scientists can map your brain activity, trace the neural pathways that correlate with thoughts and emotions, measure the electrical storms that accompany dreams and decisions, but the essential mystery remains. How does matter become aware of itself? How do neurons firing in patterns create the subjective experience of colour, sound, emotion, thought? This is the hard problem of consciousness, and it would be just as hard in an inward expanding universe, but it might be framed differently, understood through different metaphors, approached from different angles. In our expanding universe, consciousness seems like an anomaly, a tiny pocket of organisation and awareness in a cosmos trending toward disorder and dispersal. We are temporary patterns maintaining ourselves against the tide of entropy, brief flames of awareness burning in an increasingly cold and empty universe. This cosmic context inevitably influences how we think about ourselves, how we understand our place in the grand scheme, how we interpret the meaning and purpose of consciousness. We see ourselves as fighting against cosmic dissolution, maintaining our coherence despite universal expansion, creating meaning in a universe that seems indifferent to meaning. But imagine consciousness arising in an inward expanding universe, where the cosmic tide flows toward gathering rather than dispersal, where the universe itself seems to be drawing together, concentrating, perhaps even organizing itself on the larger scales. Conscious beings in such a universe might see themselves not as anomalies, but as harmonious expressions of a cosmic tendency toward convergence. Their awareness might feel less like a candle flame in the darkness, and more like a note in a vast symphony that's gradually bringing all its themes together, a local manifestation of a universal principle of gathering and integration. Memory, that foundation of identity and continuity, takes on interesting dimensions when we consider it in the context of cosmic expansion or contraction. Your memories are patterns encoded in neural connections, strengthened by repetition, linked by association, constantly being revised and reconstructed every time you recall them. In a very real sense, you are gathering your past into your present, drawing together dispersed moments into a coherent narrative of self. This gathering of memory mirrors, in miniature, what an inward expanding universe does on the larger scales, drawing together what was dispersed, creating coherence from separation. In our expanding universe, memory works against the cosmic grain. While the universe disperses, memory gathers. While cosmic information becomes increasingly dilute, memory concentrates information. While the universe forgets its initial conditions through the erasure of expansion, consciousness remembers, holds on to the past, refuses to let go. We are islands of memory in an ocean of forgetting, maintaining our histories even as cosmic history becomes increasingly inaccessible. There's something poignant about this, something deeply human about remembering in a universe that forgets. But in an inward expanding universe, memory and cosmos would be aligned. Both would be processes of gathering, of concentration, of drawing together what was separate. The act of remembering would harmonize with the cosmic act of contraction. Conscious beings might experience memory not as a struggle against forgetting, but as a participation in universal gathering. Their personal histories would be microcosms of cosmic history, both moving in the same direction, both drawing the past into an ever richer present. The perception of time for conscious beings in such a universe deserves careful consideration. We experience time as a flow from past to future, but this experience is constructed by consciousness from memory and anticipation. We remember the past but not the future, and this asymmetry creates our sense of temporal direction. In an inward expanding universe, this basic asymmetry would remain. Entropy would still increase. Memories would still be of the past rather than the future. But the emotional colouring of temporal experience might be different. In our universe, the future often feels like dissolution, like things falling apart, like inevitable decay and separation. Even when we build and create and grow, we do so against a cosmic background of expansion and cooling. But in an inward expanding universe, the future might feel like convergence, like things coming together, like inevitable reunion and integration. The arrow of time would still point from past to future, but it would be an arrow of gathering rather than dispersal, of approach rather than retreat. Consider how this might affect the development of culture, philosophy and religion in such a universe. Human cultures in our expanding cosmos have often been shaped by a sense of loss, of paradise lost, of a fall from an original unity. Our myths speak of golden ages in the past, of decline and degeneration, of the need to preserve what we can against the forces of dissolution. Our philosophies grapple with impermanence, with the transience of all things, with the challenge of finding meaning in a universe where everything eventually disperses into cold emptiness. Cultures in an inward expanding universe might develop very different mythologies and philosophies. Instead of paradise lost, they might envision paradise approaching. Instead of decline from a golden age, they might see themselves as part of a cosmic maturation, a universal coming of age. Their religions might emphasize reunion rather than separation, convergence rather than divergence, the gathering of all things rather than their dispersal. The emotional tone of their civilizations might be fundamentally different, not the melancholy of expansion, but perhaps something else, maybe a sense of anticipation, of approaching culmination, of participating in a cosmic convergence. The nature of death would be understood differently too. In our universe, death is the ultimate dispersal, the final dissolution of the pattern that was a living being. We return our borrowed atoms to the cosmos, our energy dissipates into heat, our consciousness ceases, or transforms depending on one's beliefs. Death is aligned with the cosmic tendency toward expansion and entropy. But in an inward expanding universe, death might be seen differently, not as dispersal but as a different kind of gathering, a return to a cosmic unity that's growing stronger rather than weaker. This wouldn't make death any less final for the individual, but it might change how cultures understand and ritualize it. The emergence of life itself, that still mysterious transition from non-living chemistry to living biology, would face the same challenges in either universe. You still need the right molecules, the right conditions, the right energy flows. You still need some way for information to be stored and replicated, for metabolism to capture and use energy, for boundaries to separate living systems from their environment. But the cosmic context would be different. In our expanding universe, life emerges despite the cosmic tendency toward dispersal. In a contracting universe, life would emerge in harmony with the cosmic tendency toward gathering. This alignment might make life feel less like an accident and more like an inevitability. If the universe itself is gathering, concentrating, perhaps even organizing itself on the larger scales, then the emergence of life, the ultimate example of matter organizing itself, might seem like a natural expression of cosmic evolution rather than a rare exception to it. This wouldn't make life any less remarkable, any less complex, any less worthy of wonder, but it might make it feel less alone, less isolated, less like a brief rebellion against cosmic indifference. The development of intelligence and technology would follow similar paths but with different implications. Beings in an inward expanding universe would still discover fire, invent writing, build cities, develop science. They would still progress from stone tools to silicon chips, from walking to flying to perhaps traveling between stars. but their technological development would occur against a background of cosmic convergence rather than divergence. As their technology allowed them to reach farther into space, they would find that space itself was bringing distant destinations closer. Their expanding sphere of influence would be aided by the universe's contraction. Communication across cosmic distances would become easier over time rather than harder. In our universe, the expansion of space means that signals sent to distant galaxies take longer and longer to arrive, eventually becoming impossible as expansion carries destinations beyond the cosmic horizon. But in a contracting universe, signals would arrive sooner than expected, their journeys shortened by the contraction of space. Civilizations would find it progressively easier to communicate across cosmic distances. The universe would be helping them connect rather than forcing them apart. The search for meaning, that fundamental human drive to understand purpose and significance, would take different forms in such a universe. In our expanding cosmos, we often find meaning in local connections despite cosmic isolation, in temporary patterns despite universal dissolution, in brief moments of beauty despite the ultimate heat death awaiting everything. Our meaning is often defined in opposition to meaninglessness, our purpose carved out of an apparently purposeless universe. In an inward expanding universe, meaning might be found in participation with cosmic purpose, in alignment with universal convergence, in being part of a gathering that includes everything that exists. This wouldn't necessarily make life easier or suffering less real, but it might provide a different framework for understanding existence. Instead of creating meaning in an indifferent universe, beings might see themselves as discovering meaning in a universe that seems to have its own direction, its own tendency toward gathering and convergence. The nature of consciousness itself might be understood differently. In our universe, consciousness seems to be a local phenomenon, arising in brains, perhaps in other information processing systems, but separate and isolated from any cosmic consciousness. Each aware being is an island of experience in an ocean of non-experience. But in an inward expanding universe, with its emphasis on gathering and connection, consciousness might be seen as less isolated, more connected to other consciousnesses and perhaps to some cosmic principle of awareness. This doesn't mean consciousness would be fundamentally different in such a universe. Neurons would still fire, thoughts would still arise, experiences would still be subjective, but the philosophical interpretation of consciousness might lean toward different conclusions. Where we tend toward materialist explanations in our expanding universe, they might tend toward more integrated views. Where we see consciousness as emerging from complexity, they might see it as participating in cosmic convergence. Dreams would still occur in sleeping brains, but they might carry different cultural significance. In our universe, dreams often feel like escapes, alternate realities, departures from the waking world. In an inward expanding universe, dreams might be seen as previews, as glimpses of approaching convergence, as the mind's way of preparing for greater integration. The same neurological phenomenon, REM sleep and its associated brain activity, would be interpreted through different cultural and philosophical lenses. The development of language, that unique human ability to encode thoughts in symbols and share them with others, would be especially interesting in such a universe. Language is already a gathering phenomenon. It brings separate minds together, allows the sharing of experiences, creates collective understanding from individual thoughts. In an inward expanding universe, language might be seen as a microcosm of cosmic evolution, a local example of the universal principle of convergence. The development of global communications, the internet, the increasing interconnection of human minds through technology, might be seen as harmonious with cosmic evolution rather than as purely human achievements. Art and creativity would flourish in both universes, but might express different themes. Our art often deals with loss, separation, the passage of time, the transience of beauty. We create to preserve what would otherwise be lost, to hold on to moments that would otherwise disperse. Art in an inward expanding universe might focus more on anticipation, convergence, the approaching unity of all things. Not that their art would be uniformly optimistic, suffering and loss would still exist, but the cosmic backdrop would provide a different context for artistic expression. The concept of progress would have different implications. In our universe, progress often means building something that will eventually decay, creating order that will eventually dissolve into disorder, achieving something that will eventually be forgotten in the heat death of the universe. There's a certain futility to progress in an expanding cosmos, even if that futility is so distant as to be practically irrelevant. In a contracting universe, progress might feel more permanent, more aligned with cosmic evolution. Building something would be contributing to the cosmic gathering. Creating order would be harmonizing with universal convergence. Mental health and psychological well-being might be understood differently. In our universe, depression often involves feelings of isolation, disconnection, the sense that one is fundamentally alone in an indifferent cosmos. Anxiety often relates to uncertainty about the future, fear of dissolution, worry about things falling apart. In an inward expanding universe, psychological challenges would still exist. Brains would still have chemical imbalances, trauma would still leave scars, suffering would still be real, but the cosmic context for understanding these experiences might be different. Depression might be seen as disconnection from cosmic convergence, anxiety as fear of approaching unity. The relationship between individual and collective consciousness would be particularly interesting. In our expanding universe, we tend to see consciousness as fundamentally individual, with collective consciousness being at best a metaphor for shared culture or coordinated behavior. But in a contracting universe, with its emphasis on convergence and gathering, the boundaries between individual consciousnesses might be seen as more permeable, more temporary, more like waves in an ocean that's drawing itself together. As you lie there, perhaps feeling your own consciousness beginning to blur at the edges as sleep approaches, consider how remarkable it is that awareness exists at all, in any universe. The fact that matter can organize itself into patterns that experience, that remember, that imagine alternative universes is perhaps the deepest mystery of all. Whether the universe expands or contracts, whether it disperses or gathers, the emergence of consciousness represents something extraordinary. The universe becoming aware of itself, able to contemplate its own nature, able to imagine being otherwise. In our thought experiment, consciousness in an inward expanding universe would be much like consciousness in ours, mysterious, subjective, seemingly irreducible to pure physics, but it would exist in a different cosmic story. Instead of brief flames of awareness in an expanding darkness, conscious beings would be participants in a cosmic gathering. Instead of creating meaning against the grain of cosmic evolution, they would find meaning in alignment with it. Instead of remembering in a universe that forgets, they would remember in a universe that gathers all its history together. The beauty of consciousness, in any universe, is its ability to transcend its immediate circumstances. Even in our expanding cosmos, consciousness can imagine contraction. Even in isolation, it can conceive of unity. Even in dispersal, it can create gathering. This transcendent quality of awareness, this ability to be more than just a product of its environment, would exist in any universe. Conscious beings in an inward expanding cosmos could imagine expansion just as we imagine contraction. They could conceive of alternatives just as we do. They could wonder about the nature of consciousness just as we wonder. Here we arrive at one of the most profound paradoxes of cosmology, one that exists in both our expanding universe and our imagined contracting one. The idea that the center is everywhere and nowhere, that every point in space can legitimately claim to be the middle of everything, that the universe has no privileged location from which all else recedes or toward which all else converges. This isn't just a mathematical abstraction or a philosophical puzzle. It's a fundamental truth about the geometry of space itself, and understanding it requires us to let go of our intuitive notions about centers and edges, about inside and outside, about the very meaning of direction in a cosmos without boundaries. In our daily experience, centers are special places. The center of a circle is equidistant from all points on its circumference. The center of a city is where the important buildings cluster. The center of attention is where everyone looks. We're used to thinking of centers as unique, privileged positions that define the organization of everything around them. But the universe doesn't work this way. When we say the universe is expanding, we don't mean it's expanding from a central point like a bomb exploding in empty space. Instead, space itself is expanding everywhere simultaneously, with every point moving away from every other point, no location more central than any other. This is deeply counterintuitive. When we see galaxies moving away from us in all directions, our first thought might be that we're at the center of the expansion. But an observer in any of those distant galaxies would see exactly the same thing, all other galaxies, including ours, receding from their position. Everyone sees themselves as stationary while everything else moves away. Everyone can claim to be at the centre, which means, in a very real sense, no one is at the centre, or equivalently, everyone is. The balloon analogy helps here, but we need to be careful with it. Imagine again that expanding balloon with dots on its surface representing galaxies. As the balloon inflates, every dot sees every other dot moving away. No dot is at the centre of the expansion because the centre of the balloon is inside it, in a dimension the surface doesn't have access to. The two-dimensional surface has no centre, even though the three-dimensional balloon does. Similarly, our three-dimensional space might have no centre, even if some higher dimensional structure does. But that higher dimension isn't part of our universe, isn't somewhere we can go or point to. In our inward expanding universe, this same principle would apply but inverted. Every point would see every other point approaching, converging, drawing near, but no point would be the centre toward which everything converges. The contraction would be happening everywhere simultaneously, with every location experiencing itself as the stationary centre toward which everything else flows. It would be like water going down a drain that exists at every point simultaneously, impossible to visualize but mathematically consistent, geometrically valid. This principle, that the universe has no center, is called the cosmological principle, and it's one of the foundational assumptions of modern cosmology. It states that on large scales the universe is homogeneous, the same everywhere, and isotropic, the same in all directions. No location is special, no direction is preferred. The universe looks basically the same from any vantage point, like an infinite ocean that has waves and currents, but no shores, no center, no edge. But what does it mean, psychologically and philosophically, to live in a universe with no center? In ancient cosmologies, Earth was often placed at the center of everything, with celestial spheres revolving around us. This gave humans a special position, a privileged place in the cosmic order. The Copernican revolution displaced us from this center, showing that Earth orbits the Sun, not the other way around. Further discoveries showed that our Sun is just one star, among hundreds of billions in our galaxy just one among trillions in the observable universe. Each step removed us further from any claim to centrality. Yet in another sense, the principle that everywhere is the center returns a kind of centrality to every observer. You're at the center of your observable universe. Light from all directions has taken the same amount of time to reach you from the same distance. You stand at the middle of your own sphere of observation, your own horizon of knowledge. This isn't a privileged position in any absolute sense. Everyone else has their own observable universe centered on them. But it's your unique vantage point, your personal center, that no one else can occupy. In an inward expanding universe, this personal centrality would take on additional meaning. Not only would you be at the center of your observable universe, but you would experience everything as converging toward you, even though every other observer would experience the same convergence toward themselves. It would be like being at the bottom of a valley that exists wherever you stand, a gravitational well that moves with you, a center that you carry with you wherever you go. This raises profound questions about the nature of space itself. What kind of geometry allows every point to be the center? How can space expand or contract without having a center or edge? The answer lies in the curvature of space-time, in geometries that transcend our three-dimensional intuitions. Just as the surface of a sphere has no center, every point on Earth's surface is equally central to that surface. Higher dimensional spaces can have properties that seem paradoxical to our three-dimensional minds. The observable universe, that sphere of space from which light has had time to reach us, provides a practical kind of center. Not a center of the universe, but a center of our observation, our knowledge, our causal connection to the cosmos. In our expanding universe, this observable sphere has a radius of about 46.5 billion light-years, encompassing perhaps 2 trillion galaxies. Beyond this sphere there's presumably more universe, but we can't see it because light from those regions hasn't had time to reach us in the 13.8 billion years since the Big Bang. In an inward expanding universe, the observable universe would still be finite, still be centered on each observer, but it would grow differently over time. The contraction of space would help distant light reach us, gradually revealing more of the universe, expanding our observable sphere faster than in an expanding cosmos. The center of observation would remain with each observer, but the sphere of knowledge would grow more rapidly, encompassing more of the total universe as time passes. This brings us to a meditation on what it means to be central without being special, to be at the center of your own experience while recognizing that everyone else is equally central to theirs. It's a profound democratization of cosmic position, a recognition that every point of view is valid, every location is as good as any other for observing the universe. There's no cosmic throne, no privileged vantage point from which the universe makes more sense or appears more ordered. In our expanding universe, this principle of no center can feel isolating. If there's no center, there's no home, no special place where we belong more than anywhere else. We're adrift in an infinite ocean with no shores, no harbors, no destinations. The universe doesn't care where we are because nowhere is special. This can be liberating. We're free to make our own meaning, create our own centers, but it can also be disorienting, even frightening. In an inward expanding universe, the same principle might feel different emotionally. Yes, there's still no absolute center, but everything is converging, gathering, approaching. Instead of being nowhere special in a dispersing cosmos, you're nowhere special in a gathering cosmos. The emotional tone might be one of inclusion rather than isolation, of being gathered with everything else rather than being left behind as everything recedes. The concept of home takes on interesting dimensions in a centerless universe. Home can't be defined by cosmic position because no position is special. Instead, home becomes local, personal, defined by relationships rather than coordinates. Earth is home not because it's at the center of anything, but because it's where we evolved, where our chemistry matches the environment, where we have connections and history. In both expanding and contracting universes, home is what we make it, where we create it, not something given by cosmic geometry. But there's something beautiful about being at your own center while recognizing others are at theirs. It's a kind of cosmic empathy, a recognition that every conscious being experiences themselves as central, sees the universe from their unique vantage point, has their own valid perspective on cosmic evolution. The universe has as many centers as it has observers, each one valid, each one unique, each one seeing aspects of reality that no other perspective can capture. The night sky demonstrates this principle beautifully. When you look up at the stars, you're at the center of a sphere of observation. Every star you see is at the surface of a sphere centered on you, with the distance to the star determining how far back in time you're looking. The most distant galaxies visible through telescopes form a sphere around you, at the edge of your observable universe. You are, quite literally, at the center of everything you can see, but so is everyone else, looking up at their own night sky, centered in their own sphere of observation. In our inward expanding universe, observers would have the same experience but with a different temporal dynamic. They too would be at the center of their observable sphere, but that sphere would be revealing new galaxies more rapidly, bringing the distant universe into view more quickly. They would still be at their own center, but that center would be gathering more of the universe into its sphere of observation, like a growing circle of light in a gradually illuminating darkness. The philosophical implications of a centerless universe extend beyond cosmology into ethics, meaning and purpose. If there's no cosmic center, no absolute reference point, then meaning and purpose can't be derived from cosmic position. We can't be special because of where we are in the universe. Instead, meaning must come from what we do, how we relate, what we create. The universe doesn't provide a predetermined purpose based on position. We create purpose through our choices and actions. This is both a burden and a freedom. The burden is that we can't look to cosmic geometry for guidance, can't derive should from is, can't find purpose in position. The freedom is that we're not constrained by cosmic position, not limited by lack of centrality, not diminished by being nowhere special. Every location is equally valid for the creation of meaning, the pursuit of purpose, the experience of existence. In an inward expanding universe, beings might grapple with similar questions but from a different angle. Their universe would be gathering, converging, moving towards something. Even if that something isn't a spatial center, they might be tempted to find meaning in this convergence, to see purpose in the gathering. But they would face the same fundamental challenge. The universe provides the stage, but we write the play. The cosmos gives us the context, but we create the content. The concept of a center that's everywhere connects to deep mathematical and physical principles. In general relativity, the geometry of spacetime is described by metrics that can have various properties. Some metrics have centers, like the Schwarzschild metric describing spacetime around a black hole. Others, like the Friedmann-Lemaitre-Robertson-Walker metric describing our expanding universe, have no center. The mathematics allows for both possibilities, and observation tells us which one describes our universe. In our thought experiment of an inward expanding universe, the metric would be similar to ours but with opposite sign for the expansion factor. It would still have no center, still treat every point equivalently, still maintain the cosmological principle. The mathematics would be almost identical, just with contraction replacing expansion. The centerlessness would be preserved, the democracy of positions maintained. This mathematical equivalence of all points has profound implications for the laws of physics. The same laws apply everywhere, because everywhere is equivalent. There's no position where physics works differently, no location with special rules, no center with unique properties. This uniformity of physical law is what makes science possible. We can understand distant galaxies because they obey the same laws as laboratories on Earth. We can predict the behavior of matter anywhere in the universe because the laws don't depend on position. The search for extraterrestrial intelligence takes on interesting dimensions in a centerless universe. If there's no special position, no cosmic center where life is more likely, then life could arise anywhere conditions are suitable. We're not in a privileged location that makes us unique. We're in one of possibly countless locations where consciousness has emerged. The universe might be teeming with observers, each at the center of their own observable universe, each wondering if they're alone, each searching for others. In an inward expanding universe, this search would be aided by the contraction bringing civilizations closer together over time. But the principle would be the same. No position is special. Life could arise anywhere. Every observer is at their own center. The gathering of space wouldn't create a convergence toward a single point, but a general drawing together of all points, maintaining the democracy of positions even as distances shrink. As we contemplate this centerless geometry, whether expanding or contracting, we encounter one of the universe's most beautiful paradoxes. Everywhere is the center because nowhere is the center. Every point is special because no point is special. You're at the middle of everything you can observe while being nowhere special in the absolute scheme. This isn't a contradiction, but a deep truth about the nature of space, observation, and existence. The emotional response to this truth varies among individuals and cultures. Some find it liberating, freeing them from the burden of cosmic significance, while granting them the authority of their own perspective. Others find it disorienting, removing the comfort of absolute position while demanding they create their own meaning. But whether liberating or challenging, it's the truth of our geometric situation. We are centers without being the center, observers without being the observer, participants without being the purpose. In your own life, you experience being at the center constantly. Everything you perceive radiates from your point of observation. Every relationship extends from you to others. Every memory is encoded from your perspective. You're undeniably central to your own experience, yet you know intellectually that everyone else has the same centrality in their experience. This tension between subjective centrality and objective non-centrality is part of the human condition, part of what it means to be conscious in a universe without an absolute center. And now, as all journeys must, ours begins to curve back toward home, back toward the universe we actually inhabit with its outward expansion and cooling radiation, its galaxies sailing away into the darkness, its genuine mysteries that need no embellishment to inspire wonder. We've spent these hours together imagining an impossible alternative, a cosmos that expands inward rather than outward, and through this act of imagination, perhaps we've come to see our own universe with fresher eyes, to appreciate its particular strangeness, its specific beauty, its actual mysteries that are every bit as profound as any we could invent. Let's be clear once more, our universe does expand outward. The evidence is overwhelming, observed from countless angles, confirmed by independent methods, woven into our understanding of everything from the cosmic microwave background to the formation of galaxies. When we look at distant galaxies, we see them redshifted, their light stretched by the expansion of space. When we measure the cosmic microwave background, we find it cooling, its temperature dropping as the universe expands. When we observe Type Ia supernovae, we discover that the expansion is accelerating. driven by the mysterious dark energy that comprises most of the universe's energy density. This outward expansion is not just a feature of our universe. In many ways, it defines our universe. It sets the stage for cosmic evolution, determines the fate of galaxies, influences the formation of structures, provides the arrow of time that distinguishes past from future. Without expansion, our universe would be fundamentally different. Perhaps no galaxies would form, perhaps no stars would ignite, perhaps no planets would coalesce, perhaps no life would emerge. The expansion is woven into the fabric of everything we observe, everything we are. Yet by imagining the opposite, by spending these hours contemplating an inward expanding cosmos, we've perhaps gained a deeper appreciation for what expansion means. It's not just that space is getting bigger, it's that the universe has chosen one direction over another, one possibility over its alternative. The universe could have been static, could have been contracting, could have oscillated between expansion and contraction, but instead it expands, and expands with increasing speed, racing toward a future of ever greater distances, ever deeper isolation, ever colder darkness. The question that started our journey, what if the universe expanded inward instead of outward, has no answer in physical reality, but profound implications for how we understand that reality. By imagining the alternative, we see that our universe's properties aren't necessary but contingent, not the only way things could be, but the specific way things are. This recognition transforms our relationship with cosmic facts from passive acceptance to active appreciation, from taking things for granted to marveling at their specificity. Think about light for a moment, that cosmic messenger we've discussed at length. In our actual universe, light from distant galaxies is redshifted, arriving with less energy than it had at emission, its waves stretched by billions of years of cosmic expansion. This is just a fact, something we measure and accept. But having imagined a universe where light would be blue-shifted, compressed, arriving with more energy, we can better appreciate what redshift means. It means we live in a universe that dilutes information over time, that makes the distant past harder to observe, that gradually erases its own history through expansion. Or consider the cosmic microwave background, that faint whisper of radiation from the early universe. In our cosmos, it's cooling toward absolute zero, its photons losing energy to expansion, becoming an ever fainter echo of the Big Bang. Having imagined a universe where this radiation would be warming, gaining energy from contraction, we can better appreciate what it means to live in a universe with a cooling background. It means we live in a cosmos that's forgetting its hot birth, that's transitioning from energy-dominated to vacuum-dominated, that's writing its history in ever fainter ink. The formation of structures, galaxies, stars, planets, takes on new significance when we recognize it could have proceeded differently. In our universe, structures form despite expansion, in regions where gravity overcomes the cosmic tendency toward dispersal. Having imagined a universe where structures would form with the assistance of contraction, where gravity and cosmology would work together rather than in opposition, we can better appreciate the delicate balance in our cosmos. Our galaxies are victories against expansion, our stars are local rebellions against cosmic dispersal, our planets are tiny islands of stability in an ocean of expansion. Life itself, that most precious and mysterious phenomenon, exists in a universe that seems almost hostile to its existence. The expansion disperses matter and energy. The second law of thermodynamics demands increasing entropy. The vast distances isolate living worlds from each other. Yet life emerged anyway. Consciousness arose anyway. We exist anyway. Having imagined a universe more seemingly conducive to life, where contraction might assist the concentration of matter and energy, we can better appreciate life's achievement in our actual cosmos. We're not just alive, we're alive despite the universe's expansion, conscious despite cosmic dispersal, aware despite universal isolation. The arrow of time, that fundamental asymmetry that makes the past different from the future, points in the same direction as cosmic expansion in our universe. Both move toward greater dispersal, greater entropy, greater distance between all things. Having imagined a universe where time would still arrow forward but space would contract inward, where entropy would increase through gathering rather than dispersal, we can better appreciate the alignment in our cosmos. We live in a universe where time and space point in the same direction, where the cosmic story is one of consistent dispersal, where past and future are distinguished by expansion as much as by entropy. Our place in this expanding universe becomes more poignant when we recognize it could have been otherwise. We are brief patterns of organization in a cosmos trending toward disorganization, temporary gatherings in a universe committed to dispersal, momentary awarenesses in a cosmos heading toward eternal unconsciousness. This isn't cause for despair, but for a kind of cosmic pride. We exist not because the universe makes our existence easy, but despite the universe making it difficult. We are the universe's way of experiencing itself during this brief epoch when experience is possible. The future of our universe, that vast expanse of time stretching ahead, takes on different meaning when we consider alternatives. In our expanding cosmos, we face the heat death, that final state when all stars have died, all black holes have evaporated, all energy has been dispersed into an infinite cold emptiness. Having imagined a universe with a different future, one of gathering rather than dispersal, we can better appreciate what our future means. It means we live in a universe with an almost infinite future, but one that becomes progressively less interesting, less complex, less capable of supporting life and consciousness. But this far future is so distant as to be almost meaningless for any practical purpose. The sun will continue shining for billions of years. Our galaxy will remain intact for trillions of years. The universe will remain hospitable to life for trillions upon trillions of years. The heat death is real but so remote that it's more like a philosophical endpoint than a practical concern. We have time, vast, almost incomprehensible amounts of time, to exist, to explore, to understand, to appreciate this cosmos we find ourselves in. The discovery of dark energy, that mysterious force driving the acceleration of expansion, reminds us how much we still don't understand about our universe. We know the expansion is accelerating, but we don't know why. We can measure dark energy's effects, but we don't know what it is. Having imagined a universe with something like dark compression, driving an accelerating contraction, we can better appreciate the mystery of dark energy. It's not just another component of the universe, but a fundamental puzzle about the nature of space itself, about why the cosmos behaves as it does, about what determines the direction and rate of cosmic evolution. The questions that remain unanswered in cosmology are perhaps more beautiful than the questions we've resolved. Why does the universe expand at all? Why is there something rather than nothing? Why do the constants of nature have the values they do? Why does the universe seem fine-tuned for the existence of complexity, life, and consciousness? These questions would exist in any universe, expanding or contracting, and they point to mysteries deeper than the specific properties of our cosmos. Science continues to probe these mysteries with ever more sophisticated instruments and theories. The James Webb Space Telescope peers deeper into space and time than any previous observatory, showing us galaxies as they were when the universe was young. Gravitational wave detectors listen to the vibrations of space-time itself, hearing the collisions of black holes and neutron stars. Particle accelerators recreate the conditions of the early universe, probing the fundamental nature of matter and force. Each observation adds another piece to our cosmic puzzle, another constraint on our theories, another glimpse of the vast, strange universe we inhabit. But no matter how much we learn, there will always be room for wonder, always be space for imagination, always be value in asking what if. The universe is not diminished by our understanding, but enriched by it. Each answer reveals new questions, each discovery opens new mysteries, each observation suggests new possibilities. The cosmos is large enough, strange enough, wonderful enough to accommodate both our knowledge and our imagination, both our facts and our fantasies, both our science and our dreams. The thought experiment we've conducted together, imagining an inward expanding universe, has been more than just an exercise in creative physics. It's been a meditation on the nature of existence, a contemplation of cosmic possibilities, a way of seeing our actual universe from a fresh perspective. By imagining what isn't, we better appreciate what is. By conceiving the impossible, we better understand the actual. By dreaming of alternatives, we wake up to the wonder of reality. And what a reality it is. We live in a universe that began in a hot, dense state 13.8 billion years ago and has been expanding and cooling ever since. We live on a small planet orbiting an ordinary star in a typical galaxy among trillions of galaxies. We are made of atoms forged in the nuclear furnaces of stars, assembled by chemistry into self-replicating patterns, evolved by natural selection into conscious beings capable of contemplating our own existence. We are the universe's way of knowing itself, of appreciating itself, of imagining itself otherwise. The expansion of our universe is not just a physical fact, but a poetic truth. We're all moving apart, yet we find ways to connect. We're all becoming more isolated, yet we create communities. We're all heading toward a cold, empty future, yet we generate warmth and meaning in the present. The cosmic expansion is the background against which we live our lives, but it doesn't determine how we live them. We create gathering in a universe of dispersal. We create meaning in a cosmos without purpose. We create beauty in a universe indifferent to aesthetics. As you lie there, perhaps on the edge of sleep, feeling the weight of your body on the bed, the rhythm of your breath, the slow pulse of blood through your veins, remember that you are a part of this expanding universe, a temporary pattern in the cosmic flow, a brief awareness in the vast unconscious cosmos. You are made of star stuff, as Carl Sagan said, but more than that, you are the universe contemplating itself, imagining alternatives to itself, appreciating its own strange specificity. The universe expands outward, not inward. Space grows rather than shrinks. Galaxies recede rather than approach. Light redshifts rather than blue shifts. The cosmic microwave background cools rather than warms. These are the facts of our cosmos, the truths we've discovered through observation and theory, the realities we must accept whether we like them or not. But accepting them doesn't mean taking them for granted. Understanding them doesn't mean losing wonder at them. Knowing them doesn't mean forgetting how strange and specific and contingent they are. Our journey through an imagined inward expanding universe has been a journey of appreciation for the outward expanding universe we actually inhabit. Every difference we imagined highlights something specific about our reality. Every alternative we conceived makes the actual more vivid. Every impossibility we explored makes the possible more wonderful. We've travelled through imagination to arrive at a deeper understanding of reality, through fantasy to reach a greater appreciation of fact. The universe will continue expanding long after this night ends, long after you wake tomorrow, long after our sun dies and our galaxy collides with Andromeda, long after the last stars fade and the last black holes evaporate. This expansion is the cosmic context for everything that exists, everything that happens, everything that matters. We can't change it, can't stop it, can't reverse it, but we can appreciate it, understand it, find our place within it, and perhaps that's enough. Perhaps it's enough to be conscious in an expanding universe, to experience gathering while the cosmos disperses, to create meaning while the universe expands into meaninglessness. Perhaps it's enough to lie here on this small planet, in this ordinary galaxy, in this expanding cosmos, and simply marvel at the fact that we exist at all, that consciousness arose from unconscious matter, that the universe developed the capacity to contemplate itself, to imagine itself otherwise, to appreciate its own beautiful, terrible, specific way of being. The question we began with, what if the universe expanded inward instead of outward, has led us on a journey through space and time, through physics and philosophy, through imagination and back to reality. We've seen how changing one fundamental property of the cosmos cascades through everything else, affecting light and gravity, stars and galaxies, life and consciousness, meaning and purpose. We've used imagination not to escape reality, but to better understand it, not to reject facts, but to appreciate them more deeply. As this journey ends, as these words fade into silence, as your consciousness perhaps begins its nightly journey into sleep, carry with you this thought: the universe expands outward, and that's wonderful. Not wonderful in the sense of being optimal or perfect or designed for us, but wonderful in the sense of being worthy of wonder, deserving of awe, capable of producing beauty and complexity and consciousness despite its apparent indifference to all three. We live in an expanding universe, and that specific fact, that particular truth, that actual reality, is strange enough, beautiful enough, mysterious enough to sustain a lifetime of contemplation. The cosmos doesn't need to be otherwise to be wonderful. It doesn't need to expand inward to be worthy of awe. It doesn't need to be different to be magnificent. The universe as it actually is, expanding outward, cooling down, spreading apart, is already more strange and beautiful than we can fully comprehend. Our imagination of alternatives only serves to highlight the wonder of what is, the mystery of what exists, the beauty of the actual cosmos we're privileged to inhabit. So rest now in this expanding universe, this actual cosmos, this real reality that needs no embellishment to inspire wonder. Feel yourself held by gravity on this small world, warmed by a typical star, spinning through an ordinary galaxy in an expanding universe that somehow, against all odds, produced you. A conscious being capable of contemplating it all, the universe expands outward, carrying galaxies apart, diluting energy, heading toward heat death, and yet here you are, gathered and warm and alive, a small rebellion against entropy, a brief pattern of consciousness in the vast unconscious cosmos. This is the universe we have, the only universe we know to exist, the cosmos that actually is rather than the ones we can imagine. It expands outward rather than inward, disperses rather than gathers, cools rather than warms. These facts are neither good nor bad, neither optimal nor pessimal, neither meaningful, nor meaningless in themselves. They simply are, and we exist within them, conscious and wondering, observing and imagining, accepting reality while always asking, what if? And in that question, in that capacity to imagine otherwise, in that ability to conceive alternatives to even the most fundamental facts of existence, we find something precious. Not an escape from reality, but a deeper engagement with it. Not a rejection of facts, but a fuller appreciation of them. Not a departure from the universe, but a coming home to it. Seeing it fresh, understanding it better, marveling at its specific, contingent, actual way of being. The universe expands outward. This is the truth we return to after our journey through imagination. But we return to it changed, seeing it with new eyes, appreciating it with deeper understanding, marveling at it with renewed wonder. The universe expands outward, and we are here to witness it, to understand it, to imagine it otherwise, and through that imagination, to better appreciate the profound strangeness and beauty of the way it actually is. Sleep now, if sleep is coming. Rest now, if rest is what you need. But carry with you this gentle paradox. The universe that is more wonderful than any universe we could imagine. Not because it's perfect, but because it's actual. Not because it's designed for us, but because we emerged within it. Not because it's meaningful, but because we can create meaning within it. The universe expands outward, space grows, galaxies recede, and yet here we are, together in our solitude, connected in our isolation, finding warmth in the cooling cosmos, creating gathering in the midst of dispersal. This is our universe. This is our home. This is the cosmos we actually inhabit. It expands outward, not inward, and that simple fact contains within it all the wonder we could ever need, all the mystery we could ever explore, all the beauty we could ever appreciate. The universe is as it is, and we are as we are. And somehow in the midst of expansion, we have found each other, shared this journey, contemplated these possibilities, and returned to reality with renewed appreciation for the strange, specific, wonderful way things actually are.